Sabi na, di ka kapagungog. Walang sound.
Hello, good morning everyone. Good morning.
Morning po.
Morning po, sir.
Good morning po, sir.
Ano ba? Okay.
Naimbag mo bigat po.
Okay. So good morning everyone. So ako si Wancho. Ako yung speaker for this track on differential equations. So first and foremost, welcome to the SINISM. Ayan. So hopefully karamihan sa inyo ay soaking na namin. Okay, so this is a second part nung track on differential equation. The first one was yesterday by Dr. Macan Santos. So hopefully na-attendan nyo yung part 1 kasi I'll be using some of the ideas from part 1. Actually, yung discussion is tuloy-tuloy, no? Continuous. Okay. So for the part 2, so we're going to look at software and applets that can be used for differential equations. So here, yung class lang ng differential equation that we're going to consider will be ODE, yung ordinary differential equations. So most of you know na maraming classes ang differential equation. So like partial differential equations, stochastic, delay, etc. So sorry. So for the outline, so magbibigay muna tayo ng motivation. Ayan. So lahat naman kayo nandito, so malamang motivated na kayo. Ayan. Anyways, so we'll have 2 parts, ano? So sa talk ko we have one this morning and one on the afternoon. So for this morning, I wanted to cover yung example ng scalar differential equation. So nabanggit to yesterday, ano? So scalar, isang equation lang. So particularly, we're going to consider yung tinatawag na logistic growth. So again, this is mentioned yesterday, but we're going to look at it from dun sa goal natin na we use software. And then, so basically, we're going to use MATLAB. Ayan. So kung familiar kayo, so MATLAB is a software. So we call it MATLAB, short for Matrix Lab. Pero marami rin siyang uses. So for example, sa differential equations. And then, yung latter part, before we go to the lunch break, I'm going to show you yung friendly version na online applet. Ayan. So for those of you na hindi masyadong type yung mga codes, pwedeng applet. So particularly, this will be useful for younger students. And then yung hapon, afternoon, wala pa akong nagawang slide. But basically, I plan to cover yung planar systems, so 2D. In the morning, 1D muna ta. Then second part 2D. Siguro sa hapon din, ipakita ko yung hands-on. So during the break, kung meron kayong MATLAB, maybe you can work on dun sa code this morning. And then sa afternoon, pwede nyo itry. So maybe I will add for this one, hands-on.
Next is shooting arrays. So this is what Mar mentioned earlier.
Paki-mute po yung mic. Medyo nag-feed. Okay, so let's go to dun sa motivation. So usually, ito yung purpose natin for doing simulations. So maybe you have other purposes, pero ito yung goal natin. So yung first one is to illustrate a particular theoretical results. So for the math people, so usually you have a theoretical result, and you wanted to illustrate, yeah. So mahalagang aspeto kasi yung yung storytelling, lalo na pag teacher ka. Paano mo ikukwento na maganda. So there's a tendency talaga na usually we ibabam natin yung students with a lot of abstraction, a lot of symbols, so nakaka-overwhelm. So maybe we can do something by using illustrations. So magkwento ka using a picture. So yung keyword pala dito is this one. So sorry. So theoretical results. So before you go to simulations, so mas maganda kung meron ka ng alam dun sa problem mo before going dun sa simulations. Kasi mas magiging targeted yung method mo o yung process mo, mas maikli. Kung wala kang alam and then you jump on dun sa simulations, para kang nanghuhula. So we want to work on things more efficiently. Okay. So you have to have results muna. May na-compute ka na bago ka pumunta sa simulations. And then you seek kung tama ba yung nakuha mo. So another thing is, yun nga sabi ko, a picture is worth 1,000 words. So rather than explaining things ng mahabang kwento, pwede kang magbigay ng picture and then let the reader or the audience figure out kung ano yung information na nasa picture. Pero syempre, you have to make yung picture as informative as possible. So useless lang din yung picture kung walang information. Or may picture ka, but it will generate a lot of questions rather than answers. Yeah. Yung goal niya is to clarify yung gusto mong sabihin. So another thing about simulations is to discover further dynamics. Yeah. So yung theory mo, yung math mo, sometimes will have limitations kasi when you want to show something mathematically, baka ang dami mong kailangang gawin na tumbling. But if you have simulations, pwede mo nang gawin yung gusto mo without going through a lot of advanced math na yun lang yung gusto mo sabihin. Clear ba yan? Okay, so since most of you are teachers din, ayan. Hi ma'am pala, Ma'am Connie, teacher ko nung high school. At saka yung mga estudyante namin sa UP Baguio ngayon, na teacher na ngayon. Okay, so one of the purpose din ng simulation is to get yung images na pwede mong gamitin on other documents. So one example will be yung teaching materials. So now, naka-online tayo. So we do a lot of these slides. So gawa tayo ng PowerPoint, you need a picture. So pwede mong gamitin yung simulations. So also, pag gumagawa rin na kayo ng modules or textbook. Ayan. So maganda kung yung materials mo may magandang picture. Alam mo yan from being a student. So usually when you encounter a textbook tapos ang pangit ng picture, hindi mo ma-figure out. Ayan. So from the point of view ng student, talagang helpful yung magandang images. So yeah. And then another thing for those doing research, so when you present your research or you publish an article, so maganda na yung pictures dun sa papel mo, high quality. Ayan. Okay. Clear ba yan? Ayan. So yung goal natin for today, so we want to produce customizable vector field and trajectory plots for differential equations. Sorry. So using software, and applets. Ang problema sa applets is ito, yung customizable. So usually may mga online applets. So you input yung equation, you get the plots, pero hindi mo ma-edit yung plot. Clear. So yung gagawin natin today is we want to use software, particularly MATLAB, to do a customizable plot. Yung may gusto kang i-edit doon sa picture, gusto kong lakihan to, ibahin ang kulay. So yun yung gusto natin gawin. Ayan. So I hope on board kayo dun sa gusto natin gawin. So if you have an opportunity to learn something, so might as well jump on it. So rather than just applet na lang, pwede na. So ayan. Okay, so let me start with this example. Ito lang yata example natin for the whole morning. Ayan. So this is a scalar differential equation. Scalar kasi one equation lang siya. So this is ito yan. Okay. So yung equation na to, hindi ko alam kung anong tawag. Pero okay, sorry. Continue. Okay. So yung equation na to is tinatawag na logistic differential equation. Tama ba yan? And then yung solution niya is the logistic function. Ano. Yung logistic function was first, or at least yung earliest na documented is it's due to Verhulst, mga 1800s pa. So imagine, 1800s. So siya yata yung nag-coin ng term na logistic. Pwede nyo i-search sa Wikipedia. So yung logistic growth, usually they use it to describe a population growth. Yeah. So typically you see this equation in models in ecology, so mga population growth. Ayan. And then yung reason kung bakit siya usual na ginagamit is because maganda yung fitting niya sa data, no? So later on makikita nyo yung picture nitong logistic function, siya S shape, so sigmoidal, so para siyang exponential initially, but at some point it will have to flatten, para maging S shape. So it captures yung behavior na exponential initially, and then it will grow, and then it will magpa-flat. Okay. You've seen this equation from yesterday, but probably in a different form. When you look at the right hand side, itong part na to, no? Ito. Ayan. So when you look at the right hand side, it's actually a quadratic function, tama ba? So you can write it, itong bit na to, pwede mo siyang tignan as negative yata yung leading coefficient, and then meron kang ito, say bx. Yan siya, tama ba? So kung i-graph mo yan, you actually get a parabola that opens down, dadaan sa 0, 0. Okay. So yung reason kung bakit it was written in this form, yung merong parameters. So let me just remind you of the parameters. So yung parameters that we use here are the following. Ayan. So yung R is intrinsic growth rate. So it's a positive number. Clear? Ayan. And then yung K is the carrying capacity. So explicitly sinulat natin yung right hand side, nalalabas yung K kasi later on it will play an important role, Ayan. So yesterday na mention din itong carrying capacity, Okay. Okay. So both parameters are positive. So usually when you have a differential equation, you look for these things, Ito yung tinatawag na equilibrium solutions, or equilibrium, equilibria, or fixed point, or steady state, So anong meron sa equilibrium, So well, these are equations. So these are equations na ang derivative ay 0, But the way we should say it, these are equations that are fixed, tama ba? Or is not changing through time. Clear ba yan? So kung nandun ka sa equilibrium state, dun ka lang for all time. Yan. So sa dynamical systems, usually we are interested with invariant sets. So ito yung sets na hindi nagbabari. Yan. So one type will be equilibrium. Yan. So we look for solutions x of t where the rate of change is 0. So dapat mag-0 ito. Sorry. Dapat mag-0 ito. Clear ba? Yan. So yung derivative ay 0, pero ang derivative ay equal dito. Tama ba? So, we compute ito equal to 0. Yun, di ba? Yeah, transitivity. So, paano magsi-zero itong quantity sa right hand side? Okay. So if I look at this quantity, naka-factor na siya. So kailan siya magsi-zero? So we know from Math 17 or algebra trigo, college algebra or trigo, na kapag yung product is 0, so 1 or all the factors will be 0, no? So yung R natin, positive. So pwedeng mag-0 to. Yan. And pwede rin mag-0 ito, term na yan, or yung factor na yan. Mag-0 yung x kapag yung x is 0. Mag-0 itong nasa parenthesis kapag x is k. So you get k over k, 1 yun. Tapos 1 minus 1, 0. So ang makuha nating equilibrium solutions will be the following. Itong dalawang to. So you have x equal to 0 and x equal to k. Clear ba yan? Ayan. So, interesado tayo sa steady states. At saka, ayan. Usual na follow-up question, if you have a steady state, is it stable or unstable? So, gusto kong pag-usapan natin o discuss natin yung idea ng tinatawag na stability. So, one example siguro is the, halimbawa, yung weight mo ngayon. So, ano yung weight mo ngayon? Body weight, So, halimbawa, ang body weight mo is 100 pounds. Tama ba? 100 pounds. So, mapapansin nyo, especially if you're younger, hindi ako sure sa mga hindi younger. Pag bata ka, you have this body weight na hindi nagbabago. Halimbawa, 100 pounds ako, nagpiesta or nagpasko, nag-holiday, I ate a lot. Pero babalik ka pa din dun sa body weight mo na 100 pounds. Clear ba yan? So, ibig sabihin, yung body weight mo na 100 pounds is stable. Kasi kahit i-perturb mo siya, babalik ka dun sa body weight na yan. So, pwede mo isipin na yung body weight na yan is an equilibrium state. Clear ba? So, kahit ma-perturb siya, nagkaroon ng holiday eating or fiesta, babalik ka pa rin sa 100 pounds na weight mo. So, yung weight na yan is stable. In contrast, ano yung unstable? So, halimbawa, ang body weight mo ay 100 pounds. Tapos, nag-holiday, Christmas break, kumain ka na, naparami ka ng kain. Hindi ka na bumalik sa 100 pounds na body weight mo. Then, yung body weight na yon is unstable. Clear ba yun? So, yung idea is, if you are in equilibrium state, you perturb it a little, bumalik ka sa equilibrium state, stable yung equilibrium state. Pero kapag nag-perturb ka ng konti lang, tapos hindi ka na bumalik sa dati, hindi stable o unstable yung equilibrium state na yan. Clear ba yan? So, yun yung idea ng stability. So, we want to determine ano yung stability nitong mga equilibria. So, for this example, medyo mas madali yung analysis. So, we have the following. So, tingnan natin yung una. Bit na to. So, if you choose your x 0 to k, so it's positive number less than k, then yung rate of change will be positive. And then alam natin from calculus na kapag positive yung derivative, yung quantity is increasing. Clear ba yan? So kung yung x mo nasa 0 to k, increasing yung x. Okay ba yan? So just to recall, ito siya. So i-compute natin. So yung x ko is between 0 and k. Kita ba? It's between 0 and k. Clear ba? So anong masasabi ko din sa derivative? So when you have this inequality, kasi kailangan mo ito, di ba? Or eventually ito. Yan. So kailangan mo ng x over k. So pwede kang mag-divide ng k dito. Tama ba? So what do you get? So ang masabi mo dyan, x over k less than 1. So apparently, yung 1 minus x over k, tama ba? Ano siya? Positive? Positive, no? Yan, positive. So I hope you see yung screen. Positive siya, no? 1 minus x over k. So when you go back dun sa derivative, positive ito. Yung x ko greater than 0, positive din. So positive yung r. So positive this whole thing, positive yung derivative. Clear ba? Yeah. So let's go back dun sa statement. Sorry. Ayan. So let's go back dun sa statement dito sa baba. If x is between 0 and k, the rate of change is positive. So x is increasing. And then in contrast, kapag yung x ko naman is greater than k, kanina less than k, di ba? So if, dito na tayo sa case na to. So kapag yung x ko is larger than k, yung rate of change niya will be negative. So we know again na kapag yung derivative is negative, yung quantity is decreasing. Okay ba yan? So before k, you're increasing. After k, x is decreasing. Okay. So makita natin dito yan sa plot. Yan. Hindi ko alam kung nakikita nyo kasi may side. Sandali. Okay. Makikita ba? Okay. So dun sa picture, makita nyo, by the way, this is a plot in x at saka x dot or derivative or x prime. Okay ba yan? Ayan. So you have this parabola and then yung equilibrium is ito at saka ito. Basically ito yung red at saka yung blue. Okay. Clear ba yan? So just by graphing yung function na to in x versus x prime, you get this information. So ito yung tinitignan natin na interval kanina. Ito yung 0 to k. Ito. Yan. So pag nasa 0 to k ka, yung x mo will be increasing. Ayan, increasing. So makita nyo, kaya siya may arrow to the right kasi nag-i-increase yung x. Tama ba? And then yung sabi natin, if this is your k and then your beyond k, tama ba? Yung x is decreasing. Ayan. And then makikita nyo, meron kang arrow na pink, magenta, no? Na pa left. Ayan. Clear ba yan? And then based dun sa arrow, actually makita nyo dito, yung part na to, although negative na x dito, yung function is negative. So yung rate of change is negative. So it's decreasing dito. Ayan. So from this picture, pwede ka na mag-conclude about stability. So etong equilibrium na 0, we call it the trivial equilibrium. Ano? Pag nag-perturb ka ng konti, ano mangyayari sa kanya? Yung arrow tells you to move away. Tama ba? Yan. Clear ba? So ito yung equilibrium. So through time, nandiyan ka lang. Pero pag nag-perturb ka ng konti, say to the right, yung tendency mo is to move away kasi yung arrow pa-right. Tama ba? Yan. So, masabi natin ito. So, the trivial equilibrium is stable. Clear ba? Yan. So, may masasabi ka na agad just by looking at this picture. Ano? And then, for the other equilibrium, yung K, yung carrying capacity, anong meron dito sa equilibrium na to? So, if I perturb this point a little bit sa right, nandito ka. Yan. Ano yung tendency? Yung tendency is to go back doon sa equilibrium state. Tama ba? If I perturb it to the left, the same. Yung tendency is to move back to the equilibrium state. Tama ba? So, since kahit mag-perturb ka, you go back to the equilibrium state, we have this conclusion. So the equilibrium x equal to k is stable. Ayan. Kung naalala niyo yung example kanina, yung body weight. Ayan. So pag nag-perturb ka and then you go back to the same body weight, yung body weight na yan is stable. So it's the same idea here. Ayan. So mapapansin niyo, no, dun sa picture pa lang, marami ka nang masasabi. So importante na you give a good image to help you explain yung mga bagay-bagay. Yeah. Clear ba yan? So although you can say yung gusto mong sabihin mathematically, say etong part na to, no? Ito. So pwede mong sabihin na increasing siya, decreasing siya. Pero it helps kung meron kang picture to go with the explanation. Okay. Clear ba yan? Yeah. So apparently, this picture will tell you something about the monotone property ng x of t, ng quantity. So malalaman mo, increasing ba siya or decreasing. Tama ba? Pero alam natin, from calculus, there's more. Halimbawa, etong part na to, ano yung role nito or nito dun sa kwento natin? Alam natin na from 0 to k increasing. Pero meron ka bang pwedeng sabihin na qualitative property kung nandito ka lang or nandito ka lang? Other than increasing siya. Alam natin yan. Increasing siya dito sa 0 to k. Pero meron ka bang pwedeng sabihin na dito lang at saka dito lang? Ayan. So for those teaching calculus, alam nyo na this will give you the point of inflection. Tama? Ito. So itong bit na to will give you yung point of inflection sa graph ng x. Tama? This one will give you the point of inflection dun sa graph ng x of t. Yan. So once you compute yung solution, meron ka ng function, when you sketch it, you will see na you will get a point of inflection at half ng carrying capacity. Ayan. Actually, ang masasabi natin dito sa part na to, yung derivative is increasing. Tama ba? Increasing yung derivative. Derivative itong vertical, So pag ano siya, increasing yung derivative. Or in other words, yung second derivative, tama ba? Yung second derivative, say x prime prime positive. Tama ba? And then, ang conclusion dyan, ano? Yung graph ng x is concave up. Tama ba? So, concave up hanggang k over 2 and then dito, concave down. Pag ganun. So, makikita mo na agad yung ina-expect mo na sigmoidal or yung S-shape ng solution. Ano? Clear ba yan? Ayan. So, actually, marami kang mapipiga dun sa picture. You just have to be observant. Clear ba to? Okay. So, ito yung logistic differential equation. So, for logistic differential equation, na ganito yung itsura, we have two equilibrium solutions. We have two steady states or fixed points. Yung trivial, which is yung 0, and then you have yung K, yung carrying capacity. Nakita natin na yung trivial solution is unstable. So, ang sinasabi lang dito, say if you have a population, so kapag meron kang small population, yung tendency is to grow. Nabanggit din ito kahapon. So, if you have a small population and then you have sufficient resources dun sa environment, that it will grow. Yan. Actually, yung initial na behavior niya ng growth will be exponential. Magko-concave up siya. Diba? Yan. Hanggang dito. When you reach the point of inflection,
and then we'll see you next school year, grade 4, and have a good and safe vacation. Okay po? Bye. Thank you very much.
okay. So when you have a small population, the tendency is to increase. Initially, you're going to increase, and the rate of increase is exponential. But once you hit yung critical level, yung pag nangalahati ka na sa carrying capacity, it will still increase. Pero yung increase mo will be concave down. So medyo mag-slow down yung increase. Tama ba? Mag-increase ka pa rin. Pero bumabagal na yung pag-increase mo. Kasi concave down nga. Di ba? Yeah. So once you hit yung carrying capacity, so equilibrium state ka na. If you go beyond the carrying capacity, the tendency is to decrease. Kasi yung resources mo or yung environment, hindi niya na ma-hold yung population. So population will decrease. So yun yung idea ng logistic growth. Okay, so hopefully that's clear. Yeah. Okay. So let's compute yung exact solution, exact form ng solution ng logistic differential equation. This was done yesterday, pero iba kasi yung form. So dito we reflect yung parameter K, no? Yan. So if you will recall, so we have this differential equation, and then typically you have initial condition. So kaya nga natin siya tinatawag na initial value problem. Let's just write it down. So initial value problem. So IVP. So you have a differential equation, and then you have a starting point, or in what we call initial condition. So minsan tinuturo natin ito sa estudyante natin and it came across na parang napaka-abstract nung ginagawa, ano. But actually, what you want to say is, you have a starting point, ano, ito. And then you have a rule how this point will evolve dun sa space. So you have a point in space, and you have a rule how this point will move, ano, increasing to the left ba siya, to the right, ayan. So you have a starting point, you have a rule kung paano siya mag-move, ano. So when you tell that to the student, siguro mas less abstract yung dating sa kanya, ano, na you have a point in space na it will move, ano. Yan. Later on makikita mo to sa picture, ano, makikita mo may direction yung movement, ano, ayan. Sensya na makati yung ilong ko. Ayan. Okay. So how do we compute yung solution explicitly? So yung technique, so alam niyo na to, narinig niyo na rin kahapon. So we start with, we separate variables. Bahin niya. So starting from this bit, ano. So you separate variables. So yung mga x's sama-sama, yung mga walang x's sama-sama. Yun, di ba? And then you integrate, ano. Ayan. Clear? Yeah. So usually sinasabi ko sa class ko, ako na mag-integrate nung nasa kanan. Ito. Saan na to? Kasi mas madali yung nasa kanan, ano. So yung nasa left hand side, yung integrand, I will write it as follows, ano. Multiply ako ng k over k, k sa taas, k sa baba, and then negative. Tapos may negative din doon. Ayan. Kasi later on, kailangan ko nung negative sa r. Ayan. Clear ba yan? And also, para maging ganito yung itsura ng factor, x minus k instead of k minus x. Diba usually, we write it una yung variable. Okay. Clear ba yan? And then, we use yung tinatawag na partial fraction. Ano? So, etong bit na to, itong fraction na to, we write it as follows. Ano? So, alam niyo naman yung technique paano ginagawa yung partial fractions. And then, if you get this decomposition, you can check kung tama yung, yung nakuha mo. I-combine mo ulit into a single fraction. So, halimbawa dito, ito. So, common denominator mo dyan, x at saka x minus k. I-multiply mo yon, may x ka. Tapos, negative yung ito. So, negative x minus k. So, at the end of the day, you get, ano yan, makancel yung excess sa taas. And then you're left with positive k sa taas, sa baba, yung factor. Yeah, factors. So, you go back to this form. Clear ba? So, tama. So, when you do yung partial fractions, decomposition na technique, make sure na you check na indeed you get the correct decomposition. Okay. So, yung partial fraction decomposition, it allows us to easily do the integration. Halimbawa, integral nito, tama ba? You get, ano ba, ln x minus k, tama ba? And then integral nito, ng second term, ln x, tama? So you get ln x minus k minus ln x. And then you use the property of ln to combine it into a single term. Ano? Ayan. So, for the left-hand side na integral, okay na tayo. Doon sa kanan, eto, madali lang naman to. So, meron kang negative rt plus c. Ayan. So, we do get this thing here. Ayan. Clear? And then, what we do is, we take yung exponential, tama, ng both sides. Okay. So, yung nasa left, makuha mo lang yung eto, nasa absolute value. Yung nasa right, pwede mo siya isulat as e to the minus rt times e to the c. Ayan. Clear? Ayan. We're using yung properties ng exponential. Ano? Okay, so ang makukuha natin basically when we take yung exponential will be ito. Itong bit na to. Ayan. Ayan. And then, sorry. Yung e to the c natin, we'll let it to be some constant b. Alam natin na yung b is positive. Ayan. And then, from this bit, ito, sorry. Ito. We're going to consider yung case na ano, no? Ito, x is from 0 to k. And then, pwede mo rin i-consider later on yung case na x is larger than k. So, if x is positive, sorry. So, if x is positive and less than k, ano ba yan? Anong masasabi mo dun sa quantity na nasa loob ng absolute value? Well, yung denominator, ito, positive. Yung numerator, ano siya? X minus k. So, this bit here will give you x minus k. Mag-minus k ka both sides. Ano ba? Minus k dyan, minus k dito. So, this will be less than 0 or negative. Ano? So, if you are in the interval 0 to k, yung number sa loob ng absolute value ay negative. Ano? So, ang makuha mo dyan will be x minus k over x. May negative. Ano? May negative dyan. Pero ipapasa ko yung negative sa kabila. Minus x. Sorry. Minus e. Sorry. Minus b e to the minus rt. And then from this expression, you can solve for x. Ano? So you will have x minus k equal to negative b e to the negative rt x. Pagsamahin mo yung may x sa isang side, so you get this one, 1. You get this one, pero ililipat siya. So magiging plus b e to the minus rt. And then etong negative k, pwede mo ilipat sa kabila. Yung sinasabi natin ilipat sa kabila. Pero actually, what we're doing is you add plus k dyan, plus k. So mawawala to pag 0. Pero etong plus k, you get positive k. Yan. Then dito may x ka pala. Yan. So solving for x, you get this one na. Yan. So you have k sa taas, and then you have 1 plus b e to the minus rt sa baba. Clear ba yan? Okay. So hindi ko masyado sinulat yung detailed solution, but you can follow it. So for this one, we do get this solution. Ito na yung logistic function. So we call this logistic function. Yeah. Particularly, we have this expression for b. Ano? Pwede mo siyang makuha, no? Dun sa i-explain ko lang. No? Kasi yung x at 0 natin, yung value ng x at t equal to 0 is a constant x naught. Ano? So if you use yung nakuha natin na solution, ito. So pag 0 ito, 0 yon, tama ba? Tama? So this one will give you k over 1 plus b. Tama ba? And then this is the same as x naught. So you can solve for B. Tama ba? Doon sa equation na yun. Clear? And then yung makuha mo will be this one. So yung B na yon is in terms of K and the initial condition X naught. Clear ba? And then earlier nakita nyo na itong B na to ay positive. Tama ba? Kung positive to, anong masasabi mo dito? Yung K over X naught is greater than 1 dapat para mag-positive siya. And it's indeed greater than 1, no? Kasi yung restriction na to, ito. Yan. So again, this will give you X between 0 and K. Tama. So when you compute K over X, no? So this is also X naught, sorry. So if you compute K over X naught, mag-divide ka ng K dyan, mag-divide ka ng K. Sorry. Mag-divide ka ng X naught. X naught. So you're interested with K over X naught, ano? So it's greater than 1. So when you compute for K over X naught minus 1, it's positive. No? So positive ito. Clear ba yan? Yeah. Nawala. Okay. So for this particular differential equation, apparently we can compute yung solution explicitly, and it has a nice form. Ano? Ito siya. Yan. So once you know yung function, ano? Sorry. So once you know yung function, pwede mo siyang i-graph, ano? So meron kang t at saka x. So you graph it sa t, x plane. Ano? So ito siya. Sandali lang, ano. Okay. So ito na yung logistic function, and then ito rin yung in-expect ko. Ito rin sinabi natin kanina na S shape, sigmoidal, ano. So ito siya. So you can start with a point which is x naught. Ito yon. Ito yon, ano. So it's a positive number. Ano, yan. Clear ba yan? Yan. And then okay, mahina. Mahina ba yung audio? Okay naman yung audio kasi dalawa akong account. Naka-earphone ako, so I could hear myself. Baka yung internet ka yung mabagal. Okay. Okay, so anyway, so continuing, you start with the point, and then this point will move, ano, or evolve sa space, ano. So yung space natin dito is ito, yung t versus x. So andito yung point, and then it will evolve, ano. Diba? So yung sinasabi natin na initially, yung initial stages, it will increase, and then it will increase fast kasi nga yung second derivative mo positive, concave up. So mag-increase siya mabilis. Pero after you hit yung kalahati ng carrying capacity, meron kang point of inflection. So from an increasing function or graph, it will decrease. Mag-iiba yung concavity. Concavity. Increasing pa rin siya, pero mag-change yung concavity into concave down. So mag-i-slow down yung increase. Clear ba yan? Yeah. So ang mahalagang bagay na titignan mo dito will be the following. So you need to look at the equilibrium. Ito yun, yung 0. At saka itong equilibrium na carrying capacity. So ito, alam natin kanina, unstable. Yan. So when you start close to it, tendency is to move away. Tama ba? Yan. Pero ito ang equilibrium na to is stable. If you start close to it, it will approach yung equilibrium. So stable siya. Clear? So merong qualitative behavior Ayan. And then once you hit yung point of inflection, mag-change yung concavity. Ayan. So apparently, ito yung behavior na most of the time nagmimimic nung data yung nakuha ni Verholst nung 1800. Maganda daw yung fitting nitong logistic curve Ayan. And then actually after Verholst, marami ring iba pang scientists na nakadiscover nitong logistic curve independently. Hindi nila alam yung work ni Verholst. So they discovered it differently. So ibig sabihin lang na importante itong logistic curve kasi it keeps popping out dun sa mga applications So usually they use it for population growth and also sa disease or sa medicine, they use it dun sa tumor growth yung tumor. Okay. So ang problema lang dito sa process na to, ito yung nakasulat sa baba. So yung drawback is the following. For you to graph yung trajectory or yung curve, you have to have the explicit form of the solution. Kailangan mong i-integrate. Tama ba? Ito yung process kanina. You need to compute yung solution. Clear ba? Although, na-mention din yesterday na you cannot do this for all differential equation. Maybe for the simpler ones, like this one, yung logistic equation, you can do the integration. You can do it actually by hand. And then you get this nice form of the solution. And then you can graph it. So ang problema lang talaga dito is yung integration process. So to remedy that, actually hindi naman remedy, usually complement. To complement yon is gagamit tayo ng software. Can we produce the same curve without computing yung explicit solution? Can I produce this S shape or sigmoidal function without computing mismo itong part na to. Okay, so apparently with the technology now, pwede natin gawin yon. So yung tool dito will be the following. Ito. So we're going to use MATLAB. Ito. So hindi ko alam kung familiar kayo sa MATLAB. So for some of you na familiar sa MATLAB, so maybe you're using it for other purposes. So for now, we're going to use it for differential equations. Although marami pa siyang functions. May statistical, may linear algebra, matrices, etc. Kaya nga siya matrix level. So we're going to use yung capability ng MATLAB targeted dun sa differential equations. And then we can actually produce this picture. Etong picture na to. So I hope you can see it. Okay. Nakita ba ng mas malinaw? Anong pinagkaiba nitong picture na to doon sa picture kanina? Ito yung kanina. Ayan. Anong pinagkaiba nitong first one na na-sketch natin using the explicit form of the solution compared dito sa using MATLAB? Hindi na tayo nag-compute ng solution. We sketch it using yung functions sa MATLAB. Ano yung diferensya? Okay, may sumagot sa chat si VJ. So yung difference is vector field. Yun yung sagot niya. And actually, yun yung tamang sagot. Yung difference is yung arrows. may mga arrows, may vectors. Yung vectors tells you the direction. Tama ba? Paano mag-flow? Tama ba? So if I start at this point, anong sinasabi sa akin? Mag-flow ako ng paganito. Tama ba? And then kung nandito na ako, anong sinasabi sa akin? Mag-flow ako ng paganito or paganyan. Here. So makikita mo yung arrow. This will tell you how to evolve dun sa space. Given a point, how do you evolve sa space? Yun yung differential equation. Yun yung IBP. Clear ba? Ayan. Evolution ng object dun sa space. Clear? If I start at a different point, halimbawa dito. Ayan. Anong sinasabi sa akin ng rule ng differential equation? Yung evolution. Pumunta daw ako pa ganon. Tama ba? Ayan. So kung nandito na ako, anong sinasabi sa akin? Pumunta daw akong pa ganon. So pa ganon. Tama ba? Pag nandito na ako, sabi sa akin, pumunta ka pa ganon. So pa ganon. Pag nandito na ako, punta daw pa ganon. So pa ganon. When you trace these points, actually this will give you yung solution, yung trajectory, yung curve. Clear ba? Ayan. Actually, yung nakikita nyong curve, ano yan? Bunch of points na pinagdikit-dikit. Connect the dots. Ayan. Clear ba? Importante yung direction. Clear? Kasi it tells you na yung flow is pa ganon. Ano ba? Yung flow. Hello? Hello? Ayan. Pasensya na nag-brown out. Nag-brown out dito. So maybe I'll just finish up for today's session and then later on we continue in the afternoon if we have pag nagka-power na kami. Just go back dito. So again, yung sasabi ko lang dito, you're going to get you're going to get a vector field and then it will tell you yung how to flow dun sa space. Compared dito sa previous, na wala siyang direction. Okay. Anong oras na ba? 11. Okay, so maybe I'll just go through dito sa MATLAB code, So yung goal natin for today is the following, Sorry. Okay. Hello. Narinig ba ako? Hello, medyo mahina. Okay, naririnig ako. Okay, so let's go through dun sa MATLAB, hindi ko alam kung maka-capture nyo itong codes and then if you have a MATLAB, pwede nyo gawin during the break. So, etong first step, yung nakikita nyo dito na picture actually is a several steps. Hindi siya isang code tapos makuha mo na lahat ng picture. So, isa-isa siya. So, yung first thing to do is to generate yung vector field. Yan. So, to generate the vector field, I'm going to use yung tinatawag na quiver sa MATLAB. So, ito yan. Hopefully makita nyo ang clearly yung code. Ito yan. So, we're going to use yung quiver. Okay, ibibigay ko yung lecture mamaya. Ayan. So, I'm going to use yung quiver. Yan. Na default function sa MATLAB. So, before that, what I'm going to do is etong unang line na to. So, you create a mesh. So, dun sa mesh, ito yung T, ito yung X. Yan. So, yung T ko is from 0 to 5, yung X ko from 0 to 6. Makikita nyo sa picture mamaya, ito siya. So, yung T, yung horizontal is from 0 to 5, yung vertical, 0 to 6. Okay. I'm going to make a mesh. Tapos, yung increment ko is 0.5 for both T and X. So, pwedeng mas pino yung grid nyo or pwedeng hindi. So, depende sa inyo. So, dito makikita nyo, I created points. Halimbawa ito na ang distance sa X, 0.5. Sa Y, 0.5 din. So, meron kang mesh of points or grids. Clear ba yan? Okay. So, you need those grid points. And then, you need to write down yung equation mo. Ayan. Yung R natin dito ay 2. Kung natatandaan nyo, ito yun. Tapos yung K ko ay 6. Ayan. Wala siyang meaning, just to illustrate yung how to use it in MATLAB. Ayan. So maybe kung you're looking at a particular example, you have an appropriate value for the growth rate R and the carrying capacity K. Okay. So anyways, so dito we're just going to use yung quiver. And then you have this T, X, DT, dx. So lahat to defined beforehand. Ito yung X mo, dx, dt. Yun yung T, yun yung X. Clear ba yan? Yan. So later on sa hands-on, ipapakita ko sa inyo sa MATLAB. The rest of the code, lang siya, yung pag-define lang ng frame, labels, etc. So what we're going to produce is the following, ito siya. Yan. So you get this vector field, so you have, may mga points ka, may mga lines ka, may mga slope, and then meron siyang direction. May arrow, may arrowhead. Ayan. So it tells you kung paano ka mag-flow, ang problematic dito sa part na to, compared to this one. So hopefully you see yung difference, So if you look at the vector field here, kita nyo na, compared dun sa vector field dito na na-produce natin so far, anong diferensya? So ang diferensya is may mga arrows na maliit, may mga arrows na malaki. Tama ba? At some point na maliit siya, hindi visible yung information. Hindi masyado. Unless you zoom, or okay. So to remedy that, so gagawin natin to step by step. So may mga arrows na maliit, anong gagawin ko? So yung gagawin ko will be the following, So I'm going to I'm going to normalize. So dun sa normalization, I'm just going to insert the following lines or codes. Ito. Itong part na to. Yan. Clear ba yan? Yan. So, ino-normalize mo yung vector. Hindi ko na-explain kung bakit ganyan, no? Pero apparently, this will be the vector field that you're going to get. So, yung mga arrows mo, maganda na itsura nila. Ano? Ayan. Makikita mo na yung information. Actually, dun sa taas at sa baba, no? Halimbawa dito, makita mo yung arrow sa taas, ito. Pag ganun talaga siya. No? So, kasi ito yung carrying capacity. So, pag nandito ka, you stay on that line. Ano? The same thing for 0, no? Ito. Pag nandito ka, you stay on that line. Makita mo yung arrow niya. Ano? Ayan. Diretso lang. Naka-horizontal. Pero if you choose a point in between, halimbawa dito, it tells you how to move. Tells you how to move. Ano ba? Pag ganun. Ayan. Clear ba? Ayan. So, yung first thing to do is to plot yung vector fields, a vector field. And then, mas maganda kung naka-normalize kasi mas maganda sa mata, no? And then, yung second, ayan, just to compare the two, no? Side by side. Makita mo na mas maganda yung normalize, no? Yung vectors. Okay. And then, for the trajectory, eto siya. For the trajectory, we're going to use yung MATLAB function na ODE, this one, ano? ODE 45. Ayan. So, ito yung code. So, siguro i-discuss ko lang quickly kasi naka-data lang ako. Ayan. So, we have here two functions. Ito. Ayan, at saka ito. Yung function sa baba, ang pangalan niya ay logistic function. Ano? So, dito mo na isusulat yung logistic function mo. So, ito yung R x 1 minus x over k. Ayan. So, ito yung R ko 2, yung k ko 6. Yung x ko dyan ay y1. Tapos 1 minus x over k. Clear ba yan? Ayan. So, meron kang function sa baba, no? And then, meron kang function sa taas. Yung function sa taas, it will going to use etong, asan na yun? ODE 45. So, ito ay function sa MATLAB, no? So, in order for you to use yung ODE 45, you need the following. Kailangan mong i-define yung function mo, which is naka-define na sa baba, di ba? Yun na yun. Tapos, you need the time period. So, 0 to 50. So, if you want longer time, pwede mong 1 to 2,000. Yeah. 1 to 10,000. Yeah. Pero depende dun sa computer mo kung mabagal or hindi. Usually, when you write code and then you just want to test it, small muna yung time mo para lang makita mo na tumatakbo, walang error. So, if you need longer time, yan. And then, you have this initial condition. Ito yung x naught. Yan. So, we start close to 0, 0.01, 0.1. And then, yung options, ito lang nasa taas. Yung relative tolerance, absolute tolerance. So, you can adjust it, ano. Okay. So, yan yung ODE 45. It will produce yung trajectory, ano. Itong nandito sa picture, ano. So, ang pinaplot actually dito is the following. I-explain ko lang, ano. Ito. So, we're plotting. So, ano yung pinaplot mo? Ano yung nasa horizontal? Ano yung nasa vertical? Yung nasa horizontal is ito. Yung sol x1. Actually, this is yung t. Diba? And then, for the other one, ito. This will be yung x. Yan. Diba yan? So, you're plotting t versus x. Yan. Ang maganda lang dito sa MATLAB, ano, pwede mo i-customize. You can choose yung color mo to be blue, and then pwede mo i-modify na yung line width kung gusto mong mas makapal. Ayan. Clear ba yan? Ayan. So makikita nyo dito sa picture sa right side, you have a curve na kulay blue. Medyo makapal siya, 2 yung thickness ng line. So ito yung trajectory, ano. So we produce this curve using ODE 45. Okay? So yung goal natin is to combine the two. We want the vector field together with the trajectory, ano. So yung gagawin mo lang is to, yun nga, you combine the two. And then you get this picture. Clear ba? Ayan. Kung maalala nyo, yung starting point dito ay 0.1. Yung initial condition, ano. Tapos nag-evolve siya. Tama ba? Ayan. So, ganun lang. So, you plot muna yung vector field. Make sure na naka-normalize para maganda yung itsura. And then, ipatong mo yung trajectory, yung curve. And then you get this picture. Clear ba yan? Ayan. So, ito yung code. So, kinumbine lang natin yung dalawa kanina. Kung maalala nyo dito sa code, yung lines na to, itong part na to, mula dito hanggang dito. Ayan. Ito yung para sa vector field. Ayan. Tapos yung the rest, yung pag-plot ng trajectory. Ayan. Sa trajectory. Clear ba yan? Ito yung function sa baba. Clear? And then, ang maganda dito sa MATLAB, pwede kang magkuha ng different initial conditions. Ayan. So, makikita nyo dito, meron siyang initial condition. Halimbawa ito, 0 to. Pag 0 ka, edi doon ka lang sa line na yan. The same with 6. Ito yung carrying capacity. Andun ka lang sa line na yan. But if I choose different point, halimbawa dito, so magsisigmoidal siya. Then it will approach yung carrying capacity. Here. Makita mo yung trajectory and then makita mo yung flow, no? May vector field kasi. If you start above the carrying capacity, halimbawa itong light blue, makita mo na magdi-decay lang din siya, no? To the carrying capacity. Clear ba? Ayan. Dun sa na-compute natin kanina sa solution, yung nasa baba lang, eto lang yung S-shape, yung na-plot. Pero pwede mo rin makuha later on itong nasa taas. So, dun sa MATLAB, pwede mo makuha yan. Yung trajectory, be below the carrying capacity or above the carrying capacity. No. Clear ba? Yeah. And then, dito pala sa MATLAB, you can choose yung color ng trajectories. Ano? Pwede mong piliin kung anong kulay yung gagamitin mo. Pero kung hindi mo sinabi kay MATLAB kung anong kulay ang gusto mo, siya yung mag-a-assign ng color. Halimbawa ito, nag-assign siya ng color na ganyan. So to do that, ang ginawa ko is gumamit ako ng for loop. So hindi ko alam kung familiar naman kayo sa for loop. For loop. So ang binago ko lang dito is yung initial condition. Ayan. So halimbawa, k is 1, k minus 1 initial condition. So nag-start ako at 0. Ito yon, etong part na to. Tapos ito yung trajectory. And then yung susunod dito, k is 2. So kung 2 yon, edi 1. Ito naman yon, 1. So ito yung trajectory, yung yellow, yung golden. Clear ba yan? Yan. So pwede kang mag for loop para hindi ka na mag iisa-isa na plot. So parang strategic na rin na pinili ko yung mga points na to na equally spaced. 0 to 12 na initial condition. And then I'll generate yung trajectory. So ang sinasabi ko lang dito, pwede kang mag-plot ng mas maraming trajectory and there's a option for customization. Ayan. Kung mapapansin niyo dito, binago ko na yung kulay ng vector field. Ginawa kong gray para hindi siya contrasting dun sa curves. Tama ba? Gray na siya, itong mga to. Kung napansin nyo. And then, kung napansin nyo rin, yung labels, mas malaki. Ayan. And then, particularly, yung label sa Y, nakatayo. Usually, you write it na pa ganyan, pahiga. Ayan. So, visually, mas maganda siya kung nakatayo. And also to avoid confusion, ano. We have an experience na yung nasa vertical namin ay N, letter N. So nung plinat nakaganyan. Yan. Pero nung binasa nung reviewer, akala niya Z. Yeah, mukha daw siyang Z. Pero N siya kasi nakaganon na. So yung mga maliliit na detalye na yan, so maganda na pag-isipan nyo kasi kapag yung picture mo confusing, so kailangan mong i-improve yung picture mo has to clarify rather than confuse. Okay. So last na to. So okay, so lahat naman kayo online. This is an online tool, so online applet. So you can visit this website. Mukha naman siyang safe, ayan, sana try ko yan. So pwede nyo i-type in itong website na to. And then pwede nyo i-try. Ito yung applet, i-enter mo lang yung equations mo and then it will produce yung picture na to. So get the same picture, ang wala lang talaga is yung customization. So if you need to change yung colors, yung curves, yung labels, yung scaling, ayan. Hindi mo magawa kasi assist na siya, So parang wala ka ng choice, Doon sa mga kaedad ko, ayan, alam nyo yung importance nung nung personalization. So kung inabot nyo yung panahon na nagpapatahi ka pa ng yan. Kung inabot mo yung panahon na nagpapatahi ka pa ng pantalon, makita mo ang ganda ng fit ng pantalon sa'yo. Pero nowadays, you just buy kung anong size. Makita mo may maliliit na features na ayaw mo pero okay na rin. Parang ganon. So if you want to customize, you use yung MATLAB or yung software. Pero kung ang habol mo lang is to quickly ano yung dynamics nito, quickly ano yung behavior, you can use the online tool, So if you have, depende sa purpose mo talaga. Clear ba yan? Kaso ang problema nga dito, if you're going to use yung images dun sa mga materials mo, baka mas gusto mo ng medyo enticing or medyo ayan. So dito sa website, ito siya. I-zoom ko lang. So one gagawin nyo is to i-enter mo itong equation. Ayan. Clear ba yan? Yan yung natin, yung Rx 1 minus x over k. So meron ka ng value for R tsaka k. Yung ginamit niya ditong variable ay y. So y yung sa right hand side. Clear ba? Ayan. And then make sure you use yung proper operations. So yung multiplication, asterisk, clear ba? Ayan. And then hindi ko alam kung mag-work yan pag may mga space. So bahala na kayo. Alam niyo naman yan kung hindi mag-work. Ayan. And then dito you set yung So yung horizontal kasi is t. Ay sorry. Yung horizontal is t, yung vertical is yung x. Dito y yun. So 0 to 0.043.5. So yung horizontal mo 0 to 3.5, yung vertical mo 0 to 12. Yan. Kasi yung carrying capacity natin 6, di ba? Yan. So bahala kayo mag-input niyan, So makita nyo itong picture, Yan. So yung horizontal is from 0 to 3.5 yata yun. Yung vertical is from 0 to 12. And then yung carrying capacity 6. Yan. So makikita niyo yan. Clear ba? Ayan. So pwede nyo i-try ito siguro during the break just to give you a feel, And then maybe pwede nyong paglaruan itong model. Baguhin ko yung R, baguhin ko yung K, value nun. Anong mangyayari? Meron bang qualitatively different na makikita dito? Okay. So maybe I will end with this slide, ano. And then kung may question kayo, I can answer it until 11:30 or hanggang may data ako, no. Okay. Ayan. So pwede na kayong magtanong. Hello? Wala, maliwanag ang ano lecture. Ayan. Ginagaya niyo yung mga estudyante niyo, no? Ayan. So pwede kayong magtanong ano kung ano yung pwedeng gawin. Ayan. So hindi ko alam kung paano isi-send sa niyo yung copy ng slides. Pero hopefully na-capture niyo yung ibang codes kung gusto niyo gawin sa MATLAB. Ayan. And then yung website is eto. Ayan. Sorry. Medyo mabagal. Ayan. So yung website is that one. So yung ginagamit niya na direction field, ano. It will give you yung vector field. So may direction kasi kaya direction field. Okay, may questions sa chat? Yung is MATLAB a free software? Hindi. So unfortunately yung MATLAB is a ano siya, no? Licensed software siya na medyo mahal. Hindi ko alam kung meron siyang parang free, anong tawag dito, yung pwede mo gamitin at some time just to test, ano. Or meron din yata siya yung parang student version kung gusto niyo ng mas affordable. Yan. Hindi ko alam kung meron siyang trial version. Yan. But definitely meron siyang student version if you want to buy something na cheaper. And then meron din yung non-student version. Nung binili ko yung MATLAB ko, matagal na siya, no? Nagkaroon ako ng research grant. So, ang natatandaan ko parang nasa 100,000 siya. Yung software lang for individual, ano. And then, hindi pa siya yung lahat ng, kasi may mga tools pa to. Merong tools for statistics, merong tools for other disciplines din yata. Binili ko lang yung parang basic. Nasa 100K. Yan. Pero yung license is, nagagamit ko pa hanggang ngayon. Another question sa chat, Octave po, similar software, freeware po siya. Okay. So you can also use Octave, ano? Similar siya sa MATLAB, pero freeware ang maganda doon. So, pwede niyo i-download Octave. Similar yata siya sa MATLAB, pero hindi ko alam kung yung mismong, ang tawag dito, yung mismong code would be the same, ano. I-check niyo na lang. Yan. Pero it's a nice suggestion, yung Octave, ano, sa freeware that you can use. Okay. May question pa ba? Apology, ano, nag-brown out kasi dito sa Baguio. Ayan, so siguro ang dami nag-electric pan ngayon. Nagsabay-sabay. Ayan. Ayan. Hindi ko alam kung may internet pa ako hanggang afternoon. Hindi ko maintindihan yung hindi ko maintindihan.
Good afternoon. Good morning po, sir. Narinig po ko ng audience po.
Naririnig kita pero parang ano siya, low mo.
Ako pala si Joseph Ludwig Marigben. Ay. Okay po.
Naririnig
Hello
ka
po. Sorry po. Naririnig na po.
Ayan, mas okay.
Sige, wait lang po. side po namin. So sige, ngayong time na to. So ako po pala si Joseph Ludwig Marigmen. Talk po ni Sir Wancho po, after po the topic na itutuloy po niya mamaya pong hapon, magkakaroon po tayo ng evaluation form kung saan yung pong evaluation na yun siya yung magsisilbing attendance para sa inyong pag-claim ng certificates. So remind ko lang po na dapat sa mga participants po ay at least maka 75% po kayo na complete attendance dito po sa ating track bago po kayo mabigyan po ng certificate at the end of the SINISM. Okay? So ito time check po, it's around 11:27 AM. So mag-e-end po muna pansamantala yung pong dito sa talk ni Sir Wancho ng 11:30 PM. So siguro we can entertain pa po ata sir ng ilang questions para masulit po yung hanggang 11:30.
Okay, may questions po ba? Okay, meron sa chat. Pwede po bang pasend ng link for the evaluation? Ayan.
Ayun.
Mamaya pa yata yung evaluation. So maybe we can end now, and then if you have other questions, we'll answer it this afternoon. Para to save lang din yung yung battery ko kasi brown out dito. So if you have questions, so hopefully nakuha niyo yung website kanina, and then you can email me, no? Yung email ko is ito. Ayan. So if you have questions or gusto niyo nung copy nung ayan. Pero alam ko magbibigay yung SINISM nung copy ng mga slides, na minsanan lang. So you can email me if you have questions or if you want to request the documents. Okay, so maybe we can end now, and then we continue this afternoon at 1 PM. Thank you for
Okay
coming.
po. Yes po
Enjoy
sir.
your meal.
Bali 1 PM po.
Okay, 1 PM. Thank you.
Okay po. Sir, maraming salamat po. Bali, sa sisave po ng data, pwede muna po kayong mag-log out po pansaman for discussion po. Okay? So, let's log out muna po tayo guys, tapos balik po tayo ng 1 PM po. Maraming salamat po.
Thank you din. Enjoy your meal. Hello. Good afternoon. Good afternoon. Naririnig ba ako? Yan. Hello. Okay. May nag-chat si Ate Mitch. Okay, good afternoon, ano? So maybe we can start now, ano, and then baka mawala ulit yung kuryente. Okay, so just to recap, ano, yung diniscuss natin kaninang umaga. So, we look at one particular example ng scalar differential equation, yung logistic differential equation, and then so we did some analysis, ano, before jumping dun sa software o sa simulations. So usually yung ginagawa dito, so you compute yung equilibrium, and then maybe you can say something about yung stability ng equilibrium, ano, yan. And then so apparently we can compute it explicitly, so by hand yung solution, we can plot it, ano. And then merong mga qualitative information dun sa plot, ano. So yung halimbawa yung increasing niya, ano pa yung point of inflection, etc. Okay. So apparently yung drawback nga is you need to do the integration, ano. So in case you can't do the integration, you can use software. So one example will be MATLAB, ano. So yung MATLAB kasi ito yung mas pinaka-familiar sa akin na software. So that's why I'm using it, ano. Okay. So particularly for MATLAB, so ginamit natin yung functions na ODE 45 at saka quiver, ano. Yung quiver will generate yung vector field. Ito yung mga arrows, ano. Then it will tell you how yung point will flow on the space, ano. And then yung ODE 45, we use it to sketch yung trajectory, yung curve, ano. And then katulad ng ginawa natin kanina, we do it step by step, ano. So we first plot yung vector field, ano. So apparently if you do it directly, medyo pangit, ano. So we did some adjustment, naging mas okay na yung itsura nung vector field. Ayan. And then we plot yung trajectory. So dito ginamit natin yung ODE 45, ano. So later on sa MATLAB na tayo, i-explain ko mabuti kung ano yung mga gagamitin natin, ano. Pero kanina I explain it medyo mabilis lang kasi ano, nag-brown out. Ayan, so we plot yung trajectories. Ayan. And then we combine the two, ano. Mas maganda yung itsura niya kapag may vector field tapos may trajectory, ano, mas kumpleto, ano. Ayan. So makikita niyo naman. So when you look at the code, you should be able to identify ano yung lines na will do the vector field, ano yung lines na will give you the trajectory, no. And then you can see may mga usual practices pag nagsusulat ka ng code, ano. Yung susunod sa akin na lecturer, si Dr. Peralta, will discuss yung mga numerical methods, ano. So yeah. So usual practice when you write your code, maglagay ka ng mga comments kung anong ginagawa ng code, ano. So actually hindi yan para sa ibang tao, para sa sarili mo. So maybe you're going to look at the code maybe 3-5 years, then di mo na maalala kung ano yung ginagawa ng line na yon. So maganda na naglalagay ka ng mga comments, ano, for yourself, ano, usually. Okay. So katulad nung sinabi natin kanina, yung bentahe talaga ng paggamit ng software is yung customizable na capability. Pwede mong sorry, hindi yata naka-connect yung pencil. So you can do yung customization ng picture, ano. Ayan. So if you want to change yung kulay ng vector field into gray para mas ma-emphasize yung curve, ayan. So mga ganun ba. And then if you need to enlarge yung font ng labels or yung ibahin mo yung direction, ayan. So you can do that, ano, sa MATLAB. Okay. So another thing na pinakita ko sa inyo kanina is yung applet, ano. So we're going to do yung applet now, ano. Ayan. So may mga online mga websites na pwede nyong gamitin to also do the same thing, ano. Pero usually basic lang siya. So yung customization aspect wala masyado. Pero helpful ito kapag usually kapag student ka, wala ka masyadong background or tama ba? Gusto mo lang makita kung anong nangyayari agad-agad, immediately, ano. Pero kung ang goal mo is to write a textbook, maglalagay ka ng mga images na mas maganda sana kung ano, no, appetizing sa reader, ano. Yan. So you need to do a quality plot, ano. Yan. Maganda na ano, no, whenever we work on something, we always strive for the best. Ano yung maganda siya, ano. Kasi usually lalo na pag teacher ka, no, may tendency na kapag naging lazy ka, yung students mo will think na it's okay na to do the same thing na lazy, yung lazy solution, lazy plot, no. So maganda na laging at best yung work mo. So dito sa online applet, ano, pwede mo gawin yung the same thing, ano. Okay. So we're now moving on dun sa second part. So let me just check the time. Okay, so meron pa tayong maraming time. So we're going dun sa second part. May gagawin ko. May gagawin ng computation muna before jumping dun sa MATLAB at saka dun sa website. Kasi nagsusulat ako dito sa tablet. Later on yung software nasa laptop. So magsuswitch ako. Okay. So before jumping doon, let me just give you one example, ano. So bali, talaga magsulat. Okay. Yeah. So let's look one example dun sa planar systems, ano. So kanina scalar, isa lang yung equation mo. So ngayon 2D na tayo. So let's look at one example, ano. So example. So this will be on planar. So pasensya na sa handwriting. So yung gusto kong tignan na system is the following. Kasi gagamitin ko ito mamaya sa website. Ano, meron ding website for planar system. So I have x prime 4 minus 2y at saka y prime 12 minus 3x squared. Okay. So yung x prime dyan, ano din yan yung dx dt. Ano to yung y prime, y dy dt. Okay. Clear? Yan. So if you remember earlier, ano, yung first thing na ginawa natin is to compute yung equilibrium solutions. So for the equilibrium, Sorry. So hopefully nakita niyo. So for the equilibrium, we want to solve the following relationship. Okay, paki-silent po yung mic para. Okay, so we have, so kailangan kasi sa equilibria, di ba? Zero yung rate of change. So this should be xy such that dx dt is 0 and dy dt is 0. So we're looking for values of x and y where the derivatives are both 0. Ano? So in other words, we need to, so kung 0 to, i-0 mo ito. And then kung 0 to, i-0 mo rin ito. No? Katulad nung ginawa natin kanina. So we need to solve 4 minus 2y equal to 0 at saka 12 minus 3x squared equal to 0. Yan. So hindi naman siya mahirap na non-linear system. So we get the following equilibrium solution. So we name it E1 at saka E2. Yan. Clear ba yan? So if you solve the first equation, this one, anong makukuha mo? Actually, you get a value for y, which is 2. Ano? So actually, you will get, for the equilibrium solutions, 2 yung y component. Yan. Clear? And then if you solve for the second equation, yan. Actually, madali siya i-solve kasi isang variable lang per equation. So for the second equation, you can solve for x. Ano? Yan. So we will get 2 values for x. So these are minus 2 at saka plus 2. Yan. So hindi ko na i-spell out kung paano nakuha yung numbers na yun. Alam niyo na. Clear ba? Ayan. And then kung natatandaan nyo kanina, so we look for equilibria and then maybe we do some analysis para we can say something about their stability. Ito ba ay stable, unstable? Tama? Naalala niyo yung example kanina. Ito ba yung pag nag-perturb ako, lalayo o lalapit? Or ano? Ayan. So kung i-sketch mo ito, sorry. Ayan. Okay. So actually you need to know these things before jumping dun sa software or sa applet. Kasi otherwise kung hindi mo alam yung equilibria, saan ka titingin? Dun sa plane, saan ka magfo-focus? Clear ba 'yan? Yan. So dapat lagi kang one step ahead, na may alam ka bago ka pumunta. Otherwise maubos ang oras mo. So hindi porke may software, may solver, madali na. You have to do some parts sa human parts. Yan. And then i-complement mo with the machine. Yan. So dito sa plane, kasi nga planar system ito. So yung horizontal natin will be x value, yung y, yung vertical is y. Yan. Yan. Clear ba yan? And then if you look at the equilibrium solutions, you'll get the following. So yung isa ay 2, negative 2, sa y, positive 2 lang. Yan. So we have 2, no? Ito yung E1. Sorry, ito pala ito. Ito yung E1, yung negative 2, 2. Ano ba yan? Ito yung E1. Negative 2, 2. Si E2 ay 2, 2. I hope you see, no? Ayan. Ayan. So later on, when we use the online applet, we're just going to focus on the region near these 2 points. Clear ba yan? Hindi ka magma-minus 10 to 10. Tama? Nandun ka lang sa minus 2 to 2. mga around that number. Clear ba yan? Otherwise, kung maliit lang yung detalye na gusto mong makita, tapos tumitingin ka sa napakalaki, baka hindi mo makita yung kailangan mong makita. Ano? The same thing, ano, kapag halimbawa, naghihintayan kayo, saan tayo magkikita? SM, depth store. Pero ang laki ng depth store, may level 1 na. So you have to be specific kung saan ka lang titingin. Otherwise talagang mawawala ka or hindi mo magagawa yung kailangan mong gawin. So you have to do these things beforehand before jumping dun sa software, ano. So we need to focus from -2 to 2. Yan. So hindi ko maalala kung na-discuss kahapon yung part 1. Na-discuss yata, no? Meron yung nonlinear system and then linear system. So itong example natin now is a nonlinear system. Ito. Yeah. Clear ba yun? And then, na-discuss yata kahapon, di ba? Yung i-linearize mo and then you get linear system. And then you compute yung characteristic roots or yung eigenvalues ba yun? And then based on the eigenvalues, you will get some conclusion about the type, anong type itong equilibrium na to, ano. And then you can also say about something about their stability, stable ba siya, unstable. Yan. Clear ba yan? Yan. So outside ito sa example na to, no? Sa planar system, so nasa plane ka, no? Yan. It could happen na you get a equilibrium or a fixed point, and then you do get a trajectory. So pwedeng ganyan. So ano ba yung trajectory mo pa ganyan? Yan. Clear ba? Yan. So dito meron kang equilibrium, ang classification niya is spiral. Ano, kasi yung trajectory around it mag-spiral. Tama ba? So spiral. Yan. Kung ang trajectory ay papasok, ano siya, stable spiral. Clear ba yan? Stable spiral. And then kung palabas yung direction, pa-wind out, ano siya, unstable. Ang problema dito sa picture na to, yan, lagi kong nakikita to sa mga estudyante, no? So they will plot the point, yung equilibrium point, they will sketch the equilibrium, pero walang direction. Hindi mo alam kung yung trajectory is papasok or palabas. Clear ba? So how can you say na stable ito? How do you modify yung picture para titignan ko lang yung picture, hindi ko na kailangang magtanong pa. So lalagyan mo ng lalagyan mo ng syempre direction. Yan. Clear ba? Yan. So if you see those arrows, malaman mo na yung trajectory is converging dun sa or approaching yung point. Ano? Ayan. So indeed stable siya. Clear ba yan? Pero pag yung direction mo is palabas, di ba yun yung idea ng unstable? If you from the equilibrium, mag-perturb ka ng konti, kapag lumabas siya, lumayo, di unstable. Di ba? Pero pag nag-move ka going to the equilibrium, di stable yung equilibrium. So ito yung sinasabi ko na pwede mo i-graph yung trajectory but you need to specify yung direction. Kaya mahalaga yung vector field dun sa plotting. Ano? Ayan. Tama ba? Ayan. Otherwise, you're not gonna know ito ba ay papasok or palabas. No? Ayan. Hindi ko alam kung anong iniisip ng mga estudyante kung bakit ganyan. Pwede kang maglagay ng mas maraming detalye para mas klaro yung gusto mong sabihin. Ano? Otherwise, kung kulang yung information, there's always a tendency for misinterpretation, ano? And then confusion. Ano bang nangyayari? Okay. So we're going to do this particular example sa applet. Ano? And although pwede nyo siyang gawin sa MATLAB din kung gusto nyo i-modify yung mga i-customize yung mga parts ano. Meron din binigay na example si Dr. Macan Santos yung pendulum kung naalala niyo. Hindi ko alam kung magagawa natin. Pero let's try kasi applet lang naman so we can look at it quickly. So, yung pendulum siya. Ito yung binigay na equation kahapon. So, you have theta and then second derivative yan. And then you have R, L sine theta equal to 0. So, this is a scalar pero second order yung derivative. So, ang ginawa is to translate it into system ano. Pero first order. So, yung kung natatandaan nyo kahapon ano. Yan. Tama ba yan? O, basta yan. May theta 1, theta 2. And then theta 2 is minus R over L sin theta 1. Yun yata yan. Tama, no? Yan. So, yan yung system. Ano? So, actually, pwede kang change ka lang ng variable. Sorry. So, halimbawa, x and y na lang para mas madali. So, say this is x prime, y prime. Ano. By the way, ginagamit yung symbol na prime at saka yung dot the same way. No? Pero with respect to theta yun. So, tapos, so ano to? X prime is y na to. And then minus r over L sine x. No? So maybe we can do this planar system later on ano, dun sa applet. And then maybe we can figure out ano yung ibig sabihin ng mga trajectories in terms of the pendulum. Yun ba? Clear ba? Yan. Kung iisipin mo, di ba, yung pendulum, yung pendulum, you can have two equilibrium state, steady state. So, yung pendulum is, halimbawa ito. Nakita niyo ba? Ayan. So, meron siya yung, di ba, yung state na nasa baba lang yung pendulum. Meron din yung state na nakataas siya. Ito yung steady state, hindi gumagalaw, di ba? Equilibrium state, di ba? So, yung equilibrium na nakababa yung pendulum mo, stable ito. Kasi pag nag-perturb ka ng konti, magaganyan lang siya pero babalik ka dun sa original state. Pero yung pendulum na nakatayong ganyan, unstable itong state na to kasi pag nag-move ka ng konti, nag-perturb ka ng konti, hindi na siya babalik dun sa original na nakatayo. Di ba? Yeah. So, yung state na to is stable, yung state na to is unstable. And then meron din siyang state na periodic yung gumaganyan lang yung pendulum. Ano. Pwedeng yung pendulum mo is yung gumaganyan lang, pwede rin yung part na umiikot talaga siya. Diba? So in terms of invariant sets, meron kang equilibrium na ganito, equilibrium na patayo, tapos meron kang periodic solution na paganyan lang, na less than 180 yung swing, pwede rin yung 360 yung swing na gumaganon-ganon. Yan. So hopefully makita natin yung mga physical features na yon sa trajectories doon sa ipa-plot natin. Hindi ko alam kung magagawa natin yan. Okay. Ano ba yung gusto kong sabihin dito sa yan. Okay. Sandali lang Okay, so we're going to shift dun sa laptop So i-off ko muna itong Yan. Okay, co-host na ako. So let me just share yung screen ko. Maybe sa website. Ano ba gusto niyo unahin? Unahin na natin yung website. Okay. Nakikita niyo ba? Oo, ang nakikita ko ay Zoom. Ito siya. Okay. Ito yata yun. Okay. Nakikita niyo ba? Hello? Nakita niyo yung website?
Yes, sir.
Okay. So, etong website na to, ito yung para dun sa first example natin, ano, yung scalar. Ano, kung natatandaan nyo, so hindi ko alam kung, ayan, pwede yata lakihan. Andali ah. Ayan. Andali, lakihan ko pa. Ayan. Kita nyo? So, meron kang dy dt. Okay. Okay. Meron kang dy dt. Ito yung ano kanina, yung scalar natin na equation, pero yung x naging y. So kung natatandaan niyo yung example kanina, it's 2 yung r times x, ay sorry, y na to. And then meron kang y, 1 minus x over k, di ba? Pero y dito, y over k, yung k natin 6. Oh, yun na yata yan. Ayan. Tapos kung natatandaan niyo yung t, binary natin from 0 to 5. Tapos yung x, dito y yan. Binary natin from 0 to 6. Yung 6 kasi yung carrying capacity, di ba, yung nagma-max out. Yan. So when you're done typing it, i-click niya itong graph direction field. Ayan. Ayan. So maybe i-zoom out ko lang. Ayan. So makita nyo dito sa baba, nakita ba? You get this direction field, yung mga arrows. Clear ba? Ayan. So it's the same thing na nakuha natin kanina, ano, sa MATLAB. And then to produce yung trajectories, magki-click ka lang. So i-click itong 1, 0, 1 or close to it, and then it will generate yung trajectory. Ayan. Nakita nyo, no? Kanina yung ginamit natin na initial condition ay 0.1. So halimbawa approximately here. And then you can play around. You can just click anywhere and then produce the trajectory. Ayan. Clear ba? Ayan. So hindi to ano, hindi to skill. Hindi mahirap gawin, ano. Clear. And then kung naalala nyo, di ba yung behavior sa taas may carrying capacity ka, tapos doon nagpo-flatten na yung trajectory. And then kung naalala nyo din sa gitna, yung k over 2, di ba yun yung point of inflection doon sa, ano yun? Yun yung point of inflection doon sa logistic function. Doon mag-change. Ano ba ito? Itong part na to. So at 3, itong part na to. Yan. So diyan ka may change of concavity. So from concave up to concave down. So yung rate of change is increasing initially, and then yung derivative mo will decrease, ano. Clear ba yan? So ganun lang siya. Ano. Hindi ko lang alam kung pwede nating i-try, kasi kung halimbawa nagkamali kayo ng pag-type, tingnan natin ha. Para lang din alam natin. Halimbawa wala yung parenthesis dito. Ayan. Magkakamali ba ako or pareho lang? Pareho lang. Pareho lang. Ayan. Okay, so pwede pa lang ganun. Paano pag naglagay ako ng space? Halimbawa, ayan, y times may space. Ganyan. So, ayan, hindi pwede. Ano? So make sure na you type it properly. So walang space yata. So you do get yung direction field. Pag naglagay ka ng space sa unahan, ano, ganun din. So, take note lang, ano, na, ayan, walang spaces. And then may note naman dito sa gilid, ano. So, for example, if you're using sin x, ano siya, sin parenthesis x parenthesis. Clear? Hindi siya yung sin x yan. So, baka lang magkamali ka lang. And then, kung naalala nyo, di ba kinompute natin yung equilibrium, 0 at saka k. Yung k natin dito, 6. So, it will matter kung ano yung pipiliin mong, ano to dito? Interval. Tama ba? Pili ka ng interval na nandun lang sa neighborhood ng equilibrium. Ano? Huwag masyadong malaki. Halimbawa, 0 to 6 lang naman tinitignan mo. Bakit ka magwa 100, di ba? Or 50. So, make sure na doon ka lang tumingin sa neighborhood na ano gusto mo. Halimbawa, nagkamali ka, gawin natin tong, gawin natin 50 at saka 60. Yan, so. Makikita nyo naman. Ayan siya. Ayan. So, i-click ka dyan, yung trajectory. So, ang sinasabi ko lang, you have to know beforehand. You have to have some information na it will guide you kung ano yung gagawin mo, di ba? Otherwise, talagang manghuhula ka. Ano? So, imagine, ano. Yan. So, halimbawa, masyadong malaki yung Y mo. Halimbawa, 600. Yan. So, pag tinignan mo yung picture, parang, anong nangyayari? Di ba? Parang, lahat sila pababa. So, hindi mo yung makita yung gusto mo ba? Ayan. So, kailangan may gawin ka beforehand. Ano? Ayan. So, that one is for the, direction field. Ano? Ayan. So, makikita nyo naman dito may notes. Ano? Yung direction field plotter, meron siya yung, ano, no? Yung original na website kay John Paul King. Ano, eto. Pero hindi na yata siya nag-work. Hindi ko alam kung. Yan. Clear ba? Yan. Nung estudyante ko, long time ago, ginagamit ko tong website na to. Kasi kung gusto mo lang malaman yung immediate na behavior. Yan. Clear ba? Yan. Pero syempre, you don't expect na yung makukuha mong graph, yan, yung pwede mong i-zoom. Okay. So, another website na titignan natin is yung, nagkamali ako. Sorry. Okay. Pasensya na. Iba kasi yung rendering dito sa laptop. Natatakpan yung upper part. Okay. So another website is ito. Ito yung para sa, so let's just zoom it again. Okay. Okay. Dali medyo mabagal. Mabagal ang kalaban. Ayan. So hopefully you see yung website, ano. It's the same website pero dun sa latter part ng URL, it's ppplane. Sorry, pplane. Clear ba? Kanina D field. Ano, so this one is pplane. Ito yung nandito sa taas. Ayan. Kita ba? Okay. So, yung second example na binigay ko kanina, yung planar, yung dalawa na yung equation. Ito siya. Ito. So, kung maalala nyo, so hopefully makikita nyo, no? Medyo maliit lang. Yung x prime ay 4 minus 2y. Yung y prime ay 12 minus 3x squared. Yan. So, ganyan ko sinulat. Ano? And then, beforehand, we compute yung equilibrium solutions. And then we obtain, ano yung nakuha natin? dalawa, di ba? E1 is minus 2, 2. Tapos yung E2 is positive 2, 2. Ano? Okay. So, ito yung sinasabi ko, no? So, dali. Ito yung plane. So, XY plane ito. We're just looking at the neighborhood of the equilibria. So, 2, 2, at saka negative 2. Hindi ko na kung nakikita. Ayan. So, we're just looking at, 2, 2. So, nasan yun? Ito. Ayan. Tama, no? Tapos yung isa is at negative 2, 2. Ayan. Clear? Okay. So, hindi ko alam kung makiklik natin ito. Exactly na 2, 2. Ito yata yan. Ito ba? Ayan. Negative 2, 2. Ayun yun. Ayan. Nakita niyo yung point, ano? Tapos yung isa ay, ito ba? Ayan. Tingnan natin. Ay, iba yung lumabas sa trajectory. Ayan. Anyways, let's zoom out. Ayan. Ayan. So, nakita nyo na. Ayan. So, we're just interested around that neighborhood of the equilibrium. Halimbawa, itong 2, 2. Ano? So, pwede nyo i-click. Halimbawa, ito. Ayan. Clear ba? And then, dito rin sa taas. Sa baba, meron na. Sa left. Ayan. Clear ba? Ayan. So, maganda itong applet, online applet. So, it can show you the vector field, and then it will show you the trajectories. Ayan. So, tingnan natin, ano. Nalilito na ako. Halimbawa, ito. So, ay, sandali. Dali, Okay. Halimbawa, itong E1, yung negative 2, 2. Equilibrium siya, di ba? Pag nandun ka sa mismong point na yon, through time, nandun ka lang. So, tama ba? Pero if you perturb a little, halimbawa dito, ano mangyayari sa'yo? Ayan. So, may trajectory, di ba? Yung trajectory is, ano siya, cycle, orbit, close orbit. Tama ba? Ayan. For this equilibrium, yung trajectories around it, close to it, are cycles. Paikot. Yan. So, katulad nito, cycle. So, in terms of, sorry, may bagyo ba? Pakimute po yung mic. Okay. So, yung trajectory, yan, close cycle, orbit. And then, makita mo, yung direction, ano siya, paikot. Particularly, ano siya, counterclockwise. Tama? So, you know that from the vector field. Ano? In terms of classification, ano siya? Stable ba siya? Unstable? Ano yung classification natin kanina? Kapag yung trajectory lumayo sa equilibrium, edi unstable. Lumayo ba siya? Hindi. Lumapit ba yung trajectory sa equilibrium? Hindi din. Paikot-ikot lang siya. Tama ba? Para siyang torpeng manliligaw. Paikot-ikot. Okay. So yung classification dito is ano yata siya, parang neutrally stable. Hindi siya unstable, definitely, kasi hindi siya lumalayo. Ano? Hindi rin siya asymptotically stable na lumalapit ka doon sa equilibrium. So it's yung usual na ginagamit is stable lang. Stable, neutral stable. Yan. Clear ba? And then if you know from your courses differential equation, yung classification ng equilibrium na to ay center point. Tama ba? You get a center point kapag yung eigenvalues mo ay purely imaginary ba? Ito yung kasi kailangan mo mag-produce ng sine cosine para umikot ka. Clear ba yan? Okay. So another equilibrium is ito. Ito yung E2 natin. Yung components niya is at 2, 2. Tama ba? Pwede ba natin i-zoom? Ay. Sorry. Yun na yata. Oh, sorry. Sagad na yan. So I'm looking at this equilibrium. Ang classification nito is a saddle point. Yung saddle point, meron siyang etong lines na to. So you have these two lines. Etong parang pa-X. Yung line na to, etong naglilin to the right. Ayan. Siya? Pag nandyan ka sa line na yan, papasok ka sa equilibrium. Makikita mo dito sa arrow na ito. Etong arrow, papasok siya, di ba? And then, looking at the arrows dito, ito, mga to, papunta siya sa equilibrium. Tama ba? If you're in that line, you tend to the equilibrium. Yung trajectory will tend or approach the equilibrium. In contrast, kung nandito ka sa line, etong pa-diagonal naman leaning to the left, makita mo yung arrow when you're on that line, yung trajectory tend to move away. Tama ba? Move away from the equilibrium. So this is a saddle point. Okay. Clear ba? So yung first na nakita natin dito is a center point. It's neutrally stable kasi hindi mo siya ina-approach asymptotically or hindi mo siya nilalayuan. Ito namang isang equilibrium, saddle point. Yung name na saddle, kung alam nyo, ito yung, di ba yung saddle na yung nasa likod ng kabayo, di ba? Yung saddle para siyang ano ba yun? Ano yung kinakain? Para siyang yung chips. Pringles. Di ba yung Pringles? Pag ano yung itsura niya. Ayan. Tama. May part siya na pag ganon, may part din na pag ganon. Ayan. And then yun, di ba yung idea ng saddle? May part na kung maglagay ka ng ball, it will move towards doon sa saddle point. Pag nasa isang direction ka. Pero pag nandun ka sa pag ganon, it will move away. So parang ganon. Ayan. So the rest of the trajectories around the saddle point, ito siya. So lalapit siya initially and then lalayo din. So pwede mo i-click. Ayan. So lalapit siya doon pero eventually lalayo din. Same thing dito, no? Kahit dito sa taas. Ayan. So lalapit, lalayo. Dito rin yata. Ayan. Clear ba? Yung papasok lang na direction is itong line na to. The rest palayo na. Okay. So it's a nice example, kasi you will get different type ng equilibrium. Okay. Clear ba? Yan. So napansin nyo na when you do these plots, these figures, dapat intentional, hindi siya yung wala kang pakialam kahit saang plane ko siya hanapin. You need to look for it at some region lang. Hindi pwede masyadong malaki. So anong ibig ko sabihin? Halimbawa, lakihan natin yung x and y. So halimbawa, minus 50 to 50. Tapos minus 50 to 100. So, ganyan siya. Then when you click, ayan. Clear ba? Ayan. So when you provide an image, make sure na yung fino-focus nyo is yung detail na gusto nyong sabihin dun sa audience. Diba? Huwag yung large. Kung gusto mong pag-usapan lang yung isang detalye, dun ka lang mag-focus. Kasi kung ibibigay mo yung malaking picture, tapos maliit lang yung titignan mo, parang hindi siya maganda. Clear ba? Okay. So that's using the applet. So okay na ba tayo? Huwag na tayong mag-MATLAB. Okay. So let's try. Ano ba to? Let's try yung pendulum. Naalala niyo yung pendulum? Tingnan natin. So yung x prime, y. Yung y prime minus RL times sin x. Okay, so minus RL times sin x. So ang problema ko dito yung RL. So suppose ano na lang siya? Ano ba? 2 na lang. Yung R over L. 2. Okay. So saan ako titingin na region? Asan yung equilibrium ko? Meron siyang 0, 0, no? 0x, 0y. Yun ba yun? Tama. Meron din yung, kailan ba mag-0 yung sign? Sa 0, x equal to 0. Saan pa? Sa pi? Multiple sa pi? Tama. So for the x component, pwede kong lakihan. Tama ba? O at least ma-cover niya yung, ano ba? 2 pi. O gawin nating 4 pi. So sa horizontal, halimbawa ano ba to? 2 pi sa left, 2 pi sa right. Okay na yan. Ano ba yung 2 pi? Mga 6. O sabihin na natin 10. Ayan. Clear ba? So you need some estimate. Sa y, ano yung estimate ko? Yung y ko ay 0 lang lagi, di ba? So something around 0. So say minus 5 to 5. Okay. Clear? Okay, let's do that. Okay. Ayan, nakikita na ba? Clear ba? Nung meron. So, kailangan natin i-click near the equilibrium. So, hindi ko alam kung... So, 1 unit yung isang scale. Tingnan nga natin. So, syempre origin. Origin. Yan. So, dapat hindi ka pasmado dito. Ayan. Tama. Tapos ano pa? Pi. Pi 0. So, mga 3.4. Ito. Tapos 2 pi. Mga 6 point something. Yun. Clear ba? Mga 3.40. Hindi rin. Tapos 6, negative 6.28. Yun. Mga ganyan. Clear ba? Yeah. So when you click anywhere, you'll produce yung mga trajectories. And then kung naalala nyo kanina, ang sabi ko, we want to interpret itong trajectories in terms of the physical state ng pendulum. Clear ba? So, asan dyan yung mga meron siyang ano dito. Andali may saddle ka dito. Ang pangit nung scaling natin. So maybe we can do masyadong malaki. So pwedeng hanggang negative pi. Kuha ba? Negative pi to 3 pi. Okay, so let's adjust. Ano ba yung negative pi? Mga negative 3.5 na lang. At saka yung 3 pi, 10, 11. Sige, mga 10.5. Okay. Equilibrium. Anyways. Meron din dito sa labas. Yan. Okay. Maybe we can say something halimbawa itong nasa origin 0, 0. Anong klaseng equilibrium siya? Anong itsura ng pendulum? So ito yata yung ano ba? Yun yung state na nasa baba lang yung pendulum. Tapos etong nasa saddle point, ito yung state na nakatayo. Clear? Tapos yung mga close orbit, etong halimbawa ito, yun yung clinic ko. Yun yung state na nagsuswing periodically. Pero maliit lang yung period. Tama ba? Yan. Tapos yung trajectory sa labas, ito yan. Yan. Yan yung state na umiikot-ikot na yung pendulum. Clear ba? Yan. So makikita mo naman. So if you study particular application and then you compute itong mga to and then you plot yung trajectories, makikita mo dapat yung physical property dun sa plots. Ayan. So yan yun sa pendulum. Ayan. Clear ba? Ayan. So yung strategy before jumping sa mga simulations, mga software, applets, dapat beforehand may alam ka na. Alam mo na kung nasan yung equilibrium, di ba? And then maybe may conclusion ka about stability, anong klase siya, center point ba siya, saddle, spiral. Yan. So clear ba? So usually when you use yung mga tools, it's just to, sabi ko nga, yung goal natin is just to illustrate a result. Pag wala kang result, wala kang illustrate. Parang nangangapa ka talaga. Yung biggest problem ng mga estudyante, gusto nilang mag-simulation pero hindi nila ginagawa beforehand. Paano ko pipiliin yung initial condition? Saan ko siya pipiliin? Kapag ito yung pinili kong initial condition, anong mangyayari sa trajectory? Anong ini-expect ko na long-term behavior? Tama? So kung maalala nyo dito, balikan ko lang ito. Sorry. Paano ba 0 to 5? Okay. Baka magamit nyo din later on sa susunod na lecture. So ito yan. Pag pinili ko dito yung lagahan ko yung y, gawin kong 12. Pag pinili ko yung initial condition below the carrying capacity, ano yung ina-expect ko na trajectory, di ba? If I choose my initial condition above the carrying capacity, ano yung ina-expect ko na trajectory? Tama? if I pick my initial condition, exactly 6, ito yung carrying capacity. So, ano dito? Bawa yan, ayan. Ano yung expect kong trajectory? Di ba? Ayan. So, yung mga yon, alam mo na dapat. Ano. Pero minsan, yun sabi ko nga, yung goal din ng simulations, mga graph, baka may ma-discover ka pa na something new. Ano. Okay. Ano pa ba? Okay na tayo dito. Ayan. So if you prefer yung applets, so you can visit yung dalawang website. Yung first one is D-field para sa vector field or direction field, ano. Yan. So usually you use it for scalar, ano. And then we have the second website. This is yung para sa p-plane. Ano ba yung p-plane? Phase plane, ano. So usually you use it for planar system. So kung two equations. Clear ba? So kung 3 equations naman yon, bahala ka na sa buhay mo. Hindi, joke. Hindi, pag 3D, you can always plot in 3D. Ang problema lang talaga, mahirap siyang maintindihan pag 3D kasi ang dami mong pwedeng gawin. So if you're looking at an object na 3D, you can look at it at different angles and then you need to be on the right angle to see yung kailangan mong makita. Tama? Yeah. Pero pag plane, yan lang mas madali, ano. Hindi mas madali, mas simple. Okay. So maybe may question ba dito sa website before I move doon sa MATLAB? Okay. Wala na. Okay. So I will stop sharing this website. I will move on doon na sa MATLAB. Hindi ko alam kung nag-try kayo sa MATLAB kaninang break. Dali, i-share ko lang yung MATLAB. Ito. Okay. Bakit untitled? Sorry. Okay. Okay. So ito yung picture na nakita nyo kaninang umaga. Ito na yung pinaka-last. Ano? So ang ginawa ko dito, nag-edit na ako para mukha siyang maganda. Ano? Okay. So let me just go through again dun sa codes para ma-recall din natin. Yan. So ito. Nakikita nyo naman, ano? Manalo yung font. Sorry. Okay, so yung nasa line 3, so again, ito yung mesh grid. Tama ba? Yan. So doon sa plane, sa frame, ano ba yung frame natin dito? 0 to 3.5, 0 to 12 sa vertical. So pipili ka ng mesh grid. Ayan. Ayan. In-adjust ko na yung increment. Halimbawa ito, 0.32. So bahala kayo kung ano yung tingin nyo mas maganda. Ayan. Mamaya i-modify natin. Tapos tignan natin kung anong gawin na natin ngayon. Tingnan. Halimbawa 0.32 yung grid ay yung scale o yung increment. Gawin natin mas pino. Halimbawa 0.12. Tapos sa y, 1 yun, ano? Gawin mong 0.1. Masyadong pino. Makita nyo. Ayan siya. Nakita nyo yung Clear ba? Hindi siya masyadong maganda. Tama. Yan. So, bahala kayong mag-adjust kung ano yung gusto nyo na settings. Yan. Clear ba? Tapos, so katulad ng sinabi ko kanina, ito yung equation mo, yung logistic. Tapos nag-normalize tayo ng vectors para maganda itsura. Tapos, ayan, plinat na natin yung vector field. Yung ginamit na function dito, yung quiver. Ito. Ayan. Clear ba? So, dun sa quiver, ang ipapasok mo, t, x, dt, dx. Ayan. Clear ba yan? Which is, na-define mo na beforehand. Diba? Yung nasa previous lines. Ayan. Clear ba? Pag nakalimutan nyo kung ano yung ilalagay, dito sa command window, pwede nyong ilagay help. Help. Tapos ilagay nyo yung, yan, dapat tama spelling. Help. Tapos quiver. Yan. And then enter. So mag-output siya ng ano, no? Parang tutorial. Ano yung quiver function? Ano yung input? Ano yung output? Diba? Tapos may example. Ayan. So, yan. Clear ba? Ayan. Okay. So, dun sa quiver, kung mapansin nyo, meron yung number dito. Dun sa pinaka-last, etong part na to, which is 0.4. Ano? So, maganda na, ano, no? When you look at codes, tignan nyo kung anong nangyayari pag in-adjust. Halimbawa, itong 0.4, gawin kong 0.6. Anong mangyayari? So, try natin. Anong nangyari? Gawin kong 0.8. Ay, 0.8. Yan. Anong nangyari? Yeah. Anong nangyari? Okay, ayaw nyo sumagot. So, lumaki yung arrows. Particularly yung arrowheads. Tama ba? Ayan. So, kung gusto nyo mas prominent yung arrows, you need to adjust this number. Ayan. So, ano yung kanina? 0.4. Para pag 0.2 lang. Ayan, ganyan lang siya. So, kayo na yung mag-adjust, mag-customize ano yung mas maganda visually. Ano. Clear ba yan? Ayan. So, kung may template, wag lang kayong umasa sa template. So, try to modify it, try to improve it based on your need or needs. Ano. Okay. Ano pa ba? Ito, yung pag-plot ng trajectories or solution curves. Ano. Dito, di ba yung kanina isa lang na trajectory? Yung kulay blue. So dito, nagtry ako ng maraming initial conditions. Actually, kinuha ko yung mga integer value dito. 0 to 12. Tama. Kaya ako naglagay ng for loop dito. Clear ba? So halimbawa, ang k ko lang ay ano ba para maging point, sige, ano na lang, 0.1 ba yung kanina? So 1.1 yung k, hindi pala pwede yan. 2 lang, dapat integer yata. Integer ba? Tingnan natin kung mag-work. Ayan, isa lang. Ayan. So if k is 2, yung initial condition mo is k minus 1 yung inassign natin. So 1 lang yon. So if you start at 1, eto, yun yung trajectory. Pwede ba yung decimal? Ayan, try natin. Ayan, pwede. Clear ba? Ayan. Ang technique talaga dito, kung may tanong ka, pwede ba to? Pwede ba to? Ang sagot dyan, usually ay try mo. Ayan. Clear ba? Kung hindi ka naman ano, try mo na para masagot mo na yung tanong mo. Ang idea is, when you answer your questions on your own, mas matatandaan mo. Ano? So, umattend ka ng training, may question ka, hindi every time masasagot ng speaker. Tama ba? Maganda kung ikaw yung sasagot kasi all the more na mas matatandaan mo yung sagot dun sa tanong mo. Di ba? Kasi ang tendency nowadays, lalo na yung mga younger generation, they don't keep information kasi parang laging available. Kung may information ka, hanapin mo sa internet. No? Okay, so pwede pala yan. So ano yung kanina? 1 to 12, 13. So 1 to 13 para mag-run siya from 0 to 12. Yan. Clear? Okay. Kung ayaw mo yung makulay, pwede kang mag-adjust. So dito sa plotting, di ba itong line 25, nakita nyo? So magpa-plot ka, di ba? Yung horizontal mo ay sol.x1, yun yung t. Yung sa vertical mo, sol.y, 1, which is yung x. Ano? So pwede kang maglagay ng option for color. Yan. Halimbawa, ano, cyan. Ganun ba yan? Try natin. Ayan. Okay. So yung kulay ng trajectories, cyan. Clear ba? Minsan may mga kulay na maganda sa screen, pero once you print it on paper, iba. So, clear ba yan? Ayan. So when you're working on a module or textbook or ano man na image, so minsan maganda sa screen, pero once you print it, hindi na makita. Ayan. So strategy niyo rin yon. Pwede kayong gumawa ng graph na maganda sa screen, both sa screen and printed form. Ayan. Meron din yung maganda siya kapag colored, pero pag print mo as black and white, maganda pa din. Clear ba? So, yung customization, mahalaga, no? Depende sa inyo. Ayan, depende sa purpose nyo. So, halimbawa, gusto nyo magenta. Ayan. So, kung saan kayo masaya. Ano? Kung gusto mo na dash ba yun? Dash. Ayan. Kaso pangit. Ayan. Bahala kayo kung anong gusto yung pag-plus ba. Ayan. So, bahala kayong mag-customize. Pero pag wala kang nilagay na gusto mo, yung MATLAB yung mag-a-assign. So, ayan. Katulad nung kanina. Ayan. So, siya na yung nag-assign ng mga kulay na yan. Ayan. Preferably, ano sila? Highly distinct yung magkakadikit na kulay para madaling i-figure out kung alin yung which one is which. And then, ano pa ba? So, yun na yun. Ganun lang sa MATLAB. Yeah. So, what you can do is, yung code, ilagay nyo na dito sa editor, tapos i-save nyo, di ba? Clear ba? Or pwede mo rin i-type in sa command window, kaso pa isa-isa. Maganda kung naka-save na dito para pag mag-edit ka later on, mabilis. Clear ba yan? And then pwede ka rin mag-change ng parameter and then tignan mo kung anong mangyayari. Halimbawa, carrying capacity ko 6, baguhin ko ng 4, anong mangyayari dun sa picture? Ay, anong nangyari? Hindi ko change yung function sa baba. Ito. Yung nagpo-produce ng trajectory. Ito. Kailangan ko na i-change ito into 4. Ayun. Ayan, okay na. Clear ba? Ayan. So when you plot, make sure na meron ka nang ina-expect. And then usually kasi pag ganun, you'll know kung may mali ka sa code. Halimbawa yung kanina, inedit ko sa taas, hindi ko inedit yung function sa baba na nagpo-produce ng trajectories. Hindi sila nag-coincide. Tama ba? So alam mo na something's wrong. Clear ba? Pero pag estudyante yan, tinanong mo, bakit ganyan? Ang sagot sa'yo, yan yung lumabas eh. Guys. So, make sure na pag tinanong ka, bakit ganyan? Kasi yan yung ina-expect ko. Di ba? Hindi yung, yan yung lumabas eh. I don't care kung tama o mali, basta yan yung lumabas. So, masyado kang dependent sa tool. So, you have to have also yung human aspect na alam mo kung tama ito, may sense ba ito? Ayan, etc. So, ayun ang nangyari pag binago ko yung carrying capacity. So, paano pag binaba ko itong growth rate? Halimbawa, from 2, gawin kong 0.5. Ayan. So, ayan. Ano kaya in-expect? Ano in-expect nyo? Wala. Try natin. So, ano? Ano nangyari? Kailangan ko yatang habaan sa X, sa horizontal, sorry. So, 10 na lang. So, baba ako mag-adjust sa axis. Ayan. Ayan siya. Yeah. Clear ba? Ayan. Compared dun sa 2, yung R, mas mabagal itong mag-approach sa carrying capacity. Di ba? Yung sa first case natin, R is 2, mas mabilis siyang mag-approach dun sa carrying capacity. It makes sense kasi nga growth rate. So kung mas mataas yung growth rate mo, mas mabilis kang mag-grow. Tama. Tama. Ayan. So, and then you adjust na lang. So dito siguro i-adjust mo yung vector field. Yung tag dito, yung increment. So let's just go back dun sa yung change ko kanina. 1, 2. Okay. Ayan. So, yung picture, pwede niyo pang i-edit. Doon na sa mismong picture. So, halimbawa dito, mapansin niyo yung vector field, kulay blue, medyo blue. Gusto kong gray. So, saan ba yan? Pwede niyo i-click ito, and then i-click niyo doon sa element na gusto niyo. Halimbawa yung arrow. Ayan. Na-click na ba? Tapos right-click, color. So, pwede niyo i-change. So, kung gusto mong gray, yan. Okay. Ayan, naging gray na siya. Clear ba? Pwede niyong i-edit yung mismong picture. Ayan, mas madali siya. Halimbawa, itong Y label, gusto kong itaas. Click ko yan, tapos pwede ko i-drag sa taas. O kaya itong T, gusto kong ilagay dito. Ayan. Kita niyo ba? Sure ba? Ayan. So, pwede nyo i-customize kung anong gusto nyo. May question ba? Maliwanag. Okay. So maybe we can stop now, ano? And then kung meron kayong questions or discussions na gustong gawin, and then pwede natin gawin ngayon. Or meron kayong iniisip kung saan ko magagamit itong software, applets, saan ko magagamit. Yan. So pwede na natin i-discuss. Ano? May question ba? Dali, tignan ko saan ba nakikita yung chat dito? Ano ba yung gusto nyo malaman sa MATLAB? Dito ayun, may question sa chat. Dali, medyo mabagal. Question. Sir, regarding the MATLAB programming language, madali lang po bang intindihin? Madali ba siyang intindihin? Pwedeng oo. Pero actually, ano siya, so siguro i-share ko lang sa inyo yung experience ko sa MATLAB. Nung undergrad ako, so we have this course in numerical analysis or numerical methods. Di ba yun yung may mga i-discuss yata ni Dr. Peralta yung mga ganong type. Pero for differential equations. So meron akong course undergrad noon, numerical analysis. And then may mga programming, 'di ba, nung unang panahon. Pero yung inabutan na namin is yung C+. Ayan. So if you know C+, madali naman makapag-adapt sa MATLAB, ano. Parang sanayan lang. Ayan. Basta maganda kung meron kang background sa programming. Usually naman yung mga courses, degree courses, may programming course, at least one, di ba? Kung engineering ka, or BS Math, BS Comsci, BS Physics, usually may mga programming course. And I think nowadays, mahalaga yung skill na yun, ano? Regardless kung nasa ang discipline ka, no? Yung may mga ano kasi ngayon, mga data, ayan. Or sa statistics. Yeah. So, I know C++ dati. Tapos nung sa MATLAB kasi, may nakita akong libro, nag-self-study lang din ako, pero nandun na yung mga program ng MATLAB. Wala pa masyadong internet noon, kaya wala pa masyadong mag-google. You rely on books. So, tinitingnan mo yung mga codes doon. So, and then you try to do the exercises and then masanay ka. Ang ano lang talaga dito sa MATLAB, yung mga functions, halimbawa itong ODE 45. Ang kailangan mong malaman dito, ano ang input, ano ang output. Halimbawa ito, tignan nyo yung nasa command window. Sandali, i-adjust ko lang. Ito. So yung code natin, o yung program, logistic ang pangalan, di ba? Ito yung output niya. Di ba merong X, may Y, etc. So pwede mo i-click. Ano yung sol.x ba? Ano ba yung kanina? Hindi yata na output. Andali. Medyo mabagal. Okay. So tanggalin ko tong semicolon. Mag-output ba yung sol? Try natin. Ayun. So, merong sol. Makikita mo naman doon sa command window. Meron ba? Oh, yun yan. Ayaw pa rin. Anyways, So ang sinasabi ko lang, pag may function ka, halimbawa, ay hindi ba? Okay, pag may function ka, halimbawa, ODE 45, ang kailangan mong malaman dito, ano yung input, katulad nito, ano yung mga kailangan ko ipasok? Kailangan ibigay ko sa kanya yung function, ano ba? Ito yung dinefine ko sa baba. Ito yung logistic function. Line 30 to 33. Yan. Ano pa yung kailangan kong ibigay kay ODE 45? Kailangan mo yung function, yung time period, initial condition, at saka options na ito yung mga tolerance. Siguro ma-discuss ito dun sa next topic. Tapos ang output niya, sol. Ito. Kung makita nyo dito sa line 25, di ba may plinat? Tapos merong sol x saka sol y. Yun yung output ng ODE 45. Ina-output niya yung sol x saka sol y na kailangan mo i-plot. So ang kailangan mo lang talagang maintindihan dito, may function ka, dapat alam mo yung ginagawa, alam mo yung input-output. Halimbawa, nakalimutan mo ano yung ginagawa ng ODE 45, edi mag-help ka. So dito sa command window, kung tama ang spelling natin, help ODE 45. Ayan. Okay. So enter mo, may lalabas na information about that function. So, dali. Ayaw mag-drag. Ayan. Ayan siya. Ayan. So, basically, may information. Ayan. So, ODE 45, solve non-stiff differential equations. Ayan. Tapos, ODE 45, may input ka, ODE fun, T-span, at saka why not. Ano yung mga to? Yung T-span, initial time, final time, sa interval. Clear ba? So, nandito na lahat ng information na kailangan mo. Tapos, meron siyang output. Ano to? T-out, tsaka Y-out. Ano yung T-out? Ano yung Y-out? Andyan na din. Clear? Ayan. Tapos, may example.
Okay, thank you very much po Sir Wancho for that talk po. Siguro po sa time na to, i-post ko na po yung dun sa ating evaluation form para po sa lecture po ninyo. So, ngayon nandito na po siya sa ating chat box ng ating Zoom. So, pakiclick na lang po itong sa Google, evaluation form na link para po ma-access po ninyo sa evaluation form. Tapos, para din po sa convenience po ng lahat, okay lang po ba sir na mag-share po ako ng screen para po doon sa QR code?
Go ahead.
Okay, thank you po sir. Okay, so for the convenience of everyone, pwede po ninyong iscan ito pong sa QR code po para ma-access ninyo agad yung doon sa evaluation form. Okay, so siguro para po sa mga nalalabing minuto, meron pa po kaya po mga tanong galing po sa audience regarding po sa naging lecture discussion ni Sir Wancho?
Questions? Yeah. Kung medyo shy kayo, pwede sa chat. And then kung later on may question kayo, you can always email me. Yung email was given earlier this morning. Joseph, magbibigay ba ng copy ng slides? Sa lahat? Or?
Siguro itatanong na lang muna po sir sa committee po ng SINISM kung papayagan po na magbigay lahat ng slides.
So hindi siya default na bibigyan lahat?
Yes po sir. Opo. Hingin pa po namin sir yung permission po. Opo. Sige po. Okay, so mukhang wala naman na pong tanong galing po sa audience. So maraming salamat po muli Sir Wancho for that wonderful talk po. So
Thank
in
you
case
din.
po na meron po kayong tanong at nahihiya po kayo ngayon, pwede po ninyong i-email si Sir Wancho sa kanyang UP mail account, sa kanyang UP email po. Okay? So dahil po dyan, medyo papaga po yung ating short break. So balik po tayo mamaya pong 2:45 PM para po sa talk ni Sir Gilbert Peralta. Okay? So thank you very much po ulit sa
May
inyong lahat.
picture taking ba?
Sige. Wait lang po sir ha. I-prepare ko lang po yung sa picture taking po.
Yan, kailangan daw ng proof of life.
Okay, so in preparation for picture taking, may I request everyone to open their cameras. So
Ay, naka-share
pansamantala,
ka pa yata.
opo. I-stop share ko rin po muna po ito. Okay, thank you po. So, ayan. Tapos, ayan. Okay, handa na po ba ang lahat po para po sa picture taking? Okay. May I need your assistance po, Ma'am Trisha. Okay, at the count of 3 po, smile po tayong lahat. 1, 2, okay, ready na po ba ang lahat? Ayan. So, at the count of 3, smile po tayong lahat. 1, 2, 3, smile.
Naligo po ba tayong lahat?
Okay, second page po. Okay, third page. Okay. Pwedeng isa pa po ulit. Pakihanda po muli. 1, 2, 3, smile. Okay. Again, maraming salamat po Sir Wancho. We hope to see
Thank you
you
din.
again po sa next year's na SINISM po. Okay? Let's
Ingat
have
kayo.
Opo. Let's have a short break po tapos balik po tayo
Bye,
ng
Sir
2:45
Wancho.
PM.
Thank you.
Ayun
Okay. Good afternoon. Can you hear me? Uh, can you hear me? Okay. So good afternoon. I am Junius Wilhelm Bueno, a graduate student in UP Baguio, and I will be your moderator for the succeeding lectures. So our last lecturer, Dr. Gilbert. Sorry. Okay. Our last lecturer, Dr. Gilbert Peralta, is a professor here at the Department of Mathematics and Computer Science, UP Baguio. He obtained his doctorate in natural sciences with distinction at the Karl Franzens Universität Graz at Graz. His research interests include semi-group methods of partial differential equations, hyperbolic PDEs, optimal control PDEs, and PDEs with delay. Talked about numerical methods for ordinary differential equations. Let us welcome Professor Gilbert Peralta. Good afternoon, sir.
Okay, thank you, Mr. Bene, for that short introduction. May audio ba ako? Rinig ba?
Yes, sir.
Okay. So let me share the screen. Okay. So nakikita nyo na yung slides?
Yes, sir.
Okay, so thank you. Okay, so welcome to the last part of track C regarding differential equations. So, may nag-chat. Okay, good afternoon then. Yeah. So today we will discuss numerical methods for ordinary differential equations. So this will span the last 3 lectures of the track. Okay. So just a few comments regarding this lecture. So this will be a bit of combination of the first lecture by Dr. Macan Santos and the one given by Dr. Collera on applets and numerical softwares. So here we will discuss how can we devise methods in solving differential equations numerically, and what can we expect with these methods. So let us go to the outline of the lecture. So there are 3 parts divided, of course, in the 3 lectures. So today, our hope is to discuss 0 and 1. So first, my aim is to introduce the basic or the fundamental existence theorem regarding ordinary differential equations, and how will they play a crucial role in determining or devising these numerical methods. And then after that, we will discuss or consider single-step methods. And in the next meeting, That's tomorrow. We will talk about multi-stage and multi-step methods. Okay, so by the way, if you have questions during the talk, you could interrupt me anytime, and you can either unmute yourself or type in the chat box your questions. Yeah. So existence, uniqueness, and stability of solutions. So ano ba yung gusto natin pag-usapan dito? Of course, in the first part, during the talk of Professor Macan Santos, correct me, ayan, nag-solve kayo ng mga particular examples of ODs, right? There are several methods, like the integrating factor, a separation of variables, variation of parameters formula, if you've discussed that one, and others, okay? So in that case, you could find an explicit form of solutions, okay? But most applications, most differential equations that appear in several areas such as biology, engineering, physics, or in economics, the differential equations do not have a closed form solution. So that's why there's a call to devise, let's say, numerical methods that aims to or that aim to approximate the solutions. Okay, but of course, as mathematicians, we need to guarantee first, do we have a solution for a specific system? Okay. So let me introduce, if you're not familiar with this, the fundamental existence and uniqueness. One of the fundamental existence and uniqueness theorem for ODs is due to Picard and Lindelof. So let us consider the assumptions. So suppose I have T naught to be the initial time. So here we think of ODs as as models that evolves time, and it describes a certain phenomena. So either in biology or in physics, for instance. So the independent variable in this case would denote time, and T naught or T sub 0 would be the initial time, and T sub f would be the final time. So I have some radius r and then some initial condition u naught r. Okay. So assuming that I have a domain, okay, on the plane. So here we are just considering the case of scalar ODEs. And, I will mention later the extension to systems. Okay. So suppose I have a domain omega containing this rectangle. So think of this rectangle as what? So this is just your horizontal time. Okay. So from T naught to Tf. Okay. And then this is just some closed interval wherein the center is your initial data, u naught, okay, and r is the radius. So for technical reasons, let us suppose that I have a function f. So think of this as the right-hand side of your ODE, which encodes whatever the dynamics it want to describe. And so f is a function on omega containing the rectangle, okay, with values in r, and it satisfies this condition. So this is called the Lipschitz continuity. So there is we can find a constant LF such that the change in values of the function. So take note here, f is a function of two variables, the time, and then you can think of the second as the state. Okay. So you have time and then state. So if you take the distance between the two for a given fixed time, then the distance is magnified by, or at most magnified by the distance of the arguments, the second arguments. Okay. So assuming this is satisfied, as well as let's say, so this is the difference in time multiplied by m, capital M. So just think of this capital M as the largest function value, okay, of f, largest value of f, of magnitude of f. If this product is less than or equal to the radius of this interval here, okay, then we are guaranteed that we have a solution, and in fact it is unique to this differential equation from the time interval t naught to tf. Okay. So here, this is an existence and uniqueness theorem. So ano ba yung conditions, or what are the conditions on f? that I would guarantee that I have a solution for this ODE. Okay, and according to this theorem, it is enough to have Lipschitz continuity with respect to the second argument of your function f and continuity with respect to time. Okay. May tanong ba? So remarks. The first one that I would like to mention here is that this is in fact only a local existence theorem. Okay, so you do not have a control for R. Let's say if R is small, okay, then you need your time interval to be small. If your function has a large maximum or absolute value. Okay, so this is actually in fact a local, what we call a local existence theorem. Nevertheless, as long as your state lies in the domain omega, you can extend You can extend the solution. So the typical behavior is that you either move to the boundary and you blow up in time. Okay, so that particular behavior is sometimes observed in the study of shock waves. Yeah. So this is only a local in time existence theorem. Okay. The second remark is that, of course, there's no proof here, but if you are interested, you can look at the proof. And it is based on what we call the fixed point theorem. Okay, so, and the idea is to construct successive solutions. And in fact, that can be utilized as a starting point for approximating solutions of ODEs. Okay, but we will not go into that topic. Okay. So to cut a long story short, this theorem guarantees us that under certain conditions, we have a unique solution to this ODE. Okay. And the good thing here is that hindi natin explicitly hinanap yung solution. Okay. So that's one beauty of mathematics, wherein you can guarantee or you can show existence of an object without without constructing that object. Okay. Unless you are a constructivist, of course. Okay, so that's existence and uniqueness. So now that we have a solution, can we say that it is stable? Okay, so this ODE, you can think of this as some sort of a perturbation. We have some perturbation on the differential equation and on the initial data. Well, in reality, for example, if you go into modeling, probably you have some errors in your model, and that is encoded by this function rho. Okay, so pwedeng may noise dun sa model mo. Okay, for instance, in your parameters. Okay, in particular, if you have the classical SIR disease model. Okay, there are parameters there, and what if those parameters are not exact? Okay. So you can think of this as that error or perturbation rho. And this one is, let's say, the perturbation of the initial data. Okay, so for instance, if you gather data of your model, you will have some sort of errors. Okay, either let's say dun sa machine na ginagamit mo or sa device that you are using when you want to get the data, or human errors. Okay. For example, if you want to read data from a given device and then medyo nagkamali ka, so this can be that error. Okay. Now, so just think of this as this ODE plus the red ones. Okay, the errors or perturbation, if you like. Okay. Then stability tells us that. Okay. Now, given, of course, this is classical analysis, you still have the epsilon delta. Okay, so suppose I have a positive number epsilon. Okay, and typically this is small. Okay, and then I can find probably another small number delta in such a way that, let's say, if the error in my initial data and the error in my model is small enough, in the sense that it is less than delta, then you could check the difference. Okay, how far does the solution of the perturbed ODE is related to the exact ODE? Okay, and you can see that the maximum absolute error is less than epsilon. Okay, So put in other words, let's say if this epsilon is small, then I'm guaranteed that the solution of my perturbed ODE, or the ODE with errors, is close to the exact ODE. Okay, as long as my errors or perturbations are small enough. So this is some sort of stability or a continuity. Yeah. So small changes, small errors lead to small changes in your model. Okay. And what? In terms of applications, you like this, of course, because errors are inevitable when it comes to modeling or even in computing. Yeah. So may error parate na lumalabas. And you want to study how does your model behave under this presence of errors. Okay. So this theorem tells us that, okay, assuming the conditions for the Picard-Lindelof theorem, I'm guaranteed that my solution is stable in the sense that errors having a small magnitude lead to solutions that is close to the exact solution. Okay. I think this is only the first, probably the only proof that I will be presenting in this series of lectures, so that you will have an idea in the analysis of ordinary differential equations, beyond, of course, finding the exact solution. Okay, so what we do is here, we take the difference, okay, denoted by E. E stands for error. So let us take the difference of Z. So this Z is your perturbed solution, or the solution with error, and then minus the exact solution. So you can think of this difference as indeed the error. Now, if you subtract the ODEs, okay, or you just take the derivative, so the change in error is basically what? Okay, so this is, if you look at the two ODEs, so let us go back to the previous equations. So you subtract this by this one, okay, and so makakancel yung initial data, U naught. And then you end up with the following equation on the right-hand side. So the error satisfies this ODE. This is the difference of the right-hand sides of the ODE plus the error. Okay, and you have this initial error on the data. Okay, one classical way to look at the difference is, to study the difference is just look at the magnitude. Okay, or the distance, Euclidean distance. Yeah. So what we do is the following. So this is one of the classical methods in the analysis of ODEs. So you multiply the ODE by E. Okay, so this is this equation here. Okay, so you could see here, nagdag lang yung red na E. Okay, so that's basically multiplying this equation. Okay, and you check that this is in fact the derivative of the squared of the error divided by 2. So you just apply the chain rule to recognize that this product here is basically 1/2 times the derivative of the squared error. Okay. Yeah. Okay. So what we do is we want to bound or estimate at the right-hand side. Okay. So the first one here, we use the Lipschitz condition for F. So this one, if you apply, okay, and I will not go into the details here, but you can see that this is what less than the Lipschitz constant, which we denoted by LF a while ago, times the difference of Z and then U. Okay, so that's the difference of the second argument. But what is the difference of Z and U? That's basically the error. So you have here E squared because you have another factor E here. Okay, so that's the first term. For the second term, we deal with the Cauchy-Schwarz inequality. So I hope you are familiar with it. So the Cauchy-Schwarz inequality states that the product of two numbers is basically less than or equal to the half of the sum of the squares. Okay. So hopefully you are familiar with that. Okay, since I think this is just a start. Okay, well, that is not difficult to show. Okay. Now, instead of writing, okay, and I do not want to switch from one device to another, and I will use an online editor. Okay. So hopefully, yeah. So the one that I stated a while ago is the following. So hopefully you can see the screen. Kita ba?
Yes, sir.
Okay, thank you. So here I'm using a stock edit, wherein you could, let's say, type, if you're familiar with LaTeX, the LaTeX command, and then you could see the displayed math equations on the right. So those who are not familiar with LaTeX, you can ignore the left-hand side and just look at this right-hand side. Okay, so instead of writing, I will consider this one. Okay. So as I said, this is the Cauchy-Schwarz inequality. Yeah. The product of two numbers is less than what? The sum of or the average of the sum of the squares. Okay. Well, you can check this easily. What you do is what? Let me copy that. You just multiply two both sides. Okay. So if you multiply two, you end up with this inequality, right? Okay. 2ab is a squared plus bc. That is obviously true because what? That is, if you transpose this one to the other side, that should be minus. That would be a perfect square. Okay. So in fact, you could work backwards. Okay. So starting from this inequality, you go upwards and you get this Cauchy-Schwarz inequality, which is one of the most used inequality in analysis. And there are a lot of proofs that you could look at on the web in this case. Yeah. Pero ito yung pinakasimple. Yeah. Yeah. So that's basically what I use here. So the product of the perturbation and the error is less than the half of the sum of the squares. Okay. So I'll just combine these two here. Okay. And assuming that, let's say my error is less than delta, so you have here delta squared. Okay. So basically, you have the following differential equation, or more precisely, differential inequality. Okay. Yeah. You could cancel out 1/2 here. Okay. And this takes the form of, let's say, some sort of an exponential plus some constant here. So you could apply, let's say, integrating factor. Okay. And if you do that, okay, I will not go into the details, but after some time, you could show that, okay, the squared error is less than or equal to 1 plus delta t. So delta t here is the the time span. Okay, so that's the difference of the final time and initial time times this exponential decay. Okay, e raised to this constant, which is this constant here, times delta c squared. Delta squared. Okay, so dito use the basically the integrating factor. Okay, and we are guaranteed that the this error is small, provided that you take this delta to be small. Yeah. So that's the outline of the proof of that stability theorem. Okay, so again, if the errors are small, in the sense that it is less than delta, then the squared error over all time is also small, provided that this delta is small enough. Okay. So do you have questions? May tanong ba? Don't worry, this is only, I think, as far as I remember, the only proof that I will be considering. Okay, so that's basically existence, uniqueness, and stability. Okay. So if you notice here, we have a different approach. We considered a more general ODE. And so let us just go back. So this is what I don't like regarding pauses pagdating sa presentation. You need to go back a few slides. Yeah. So going back to this ODE, we have what studied this. We have what imposed or considered sufficient conditions that will guarantee the existence, uniqueness, and stability of solutions. Okay, without indeed constructing the solution itself. So iba na ito dun sa first lecture. Yeah. Na kung saan nagsosolve tayo to show that there's a solution. Okay, here it is more than that. Okay, and it is general. Okay, so walang a specific na F na ginamit natin dito. Okay. So this theorem has been only stated in the case of what scalar ODEs, meaning this is only a real valued function. But of course, the extension to systems of nonlinear differential equations is also valid. Okay. However, I only presented this scalar case for simplicity of presentation. Okay, now let us go to the main topic of this lecture, numerical methods for ODEs. Okay. So our goal is to solve, for instance, the solution of a given ODE. And as I said, based on experience, probably, you have solved several ODEs in your life. And you find it sometimes difficult to solve such equations because specific equations requires specific methods. Okay, so parang wala kang isang black box na kung saan you put in your ODE there and then you have the solution. Okay, so depende dun sa form ng equation yung method na gagamitin mo. Okay, and of course in reality differential equations, as I said, that arises in several applications are difficult to solve explicitly. So there's a call for numerical methods. So what we do is the following. So consider the time frame, T naught to Tf. So we divide this, so we get sample times. Okay, so let us denote the sample times by T naught, T1, and Tn. So you have here some nodes. Tn would be your final time. So n here would be the number of nodes, sampled nodes, except the initial one. Okay? And the set of temporal nodes is what? It's basically obtained from the initial node or initial time, and by adding a suitable multiples of the step size h. Okay. So in this lecture, we will only consider uniform step sizes. So in particular, we could compute the step size by what? Taking the difference between the final and initial divided by the number of nodes. Okay. So this would be your your step size. Okay. And we will denote by, the initial data by U tilde. Okay. So given this initial data, which is either the data of your ODE, the initial data of your ODE, plus some error, as I said. Okay, so if the error is, let's say, 0, then you have the exact data here. But of course, as I said, the initial data might have some error, so we need to put this quantity here. Okay. You could also think of this rho naught as an error when you want to implement your method into, let's say, certain software. Okay, so kunyari solve mo or i-implement mo yung method mo sa isang numerical software, and your initial data let's say, is a real number that is non-terminating. A classical example of that is 1/3. Okay. How do I show that one? Okay, so for example, 1/3. What if my initial data is 1/3? Then, of course, the real value of this is different from the stored value on the computer. Okay, because your computer has only a finite number of memory, so it can only store what? A finite number of trees. Yeah. So it need to cut sometime. So yung kinat niya would be the error. Okay. So when it comes to computing, in fact, these errors are inevitable. So meron at meron sila. Well, to be precise, hindi actually 3 yung ginagamit ng computer. And you know the language now. It is either zeros or ones. But I will not go into the details of that aspect. Okay. So again, as I said, you can think of this raw NAT as what? The error in storing a real number into what? A finite digit precision arithmetic. Okay. So the goal of numerical methods for ODEs aim to provide an approximation. So from now on, we will denote the approximation to be a subscript, so U sub k. So we aim to find an approximation U sub k of the solution at the time nodes, okay? For all indices from 1 to n, okay? And in general, for instance, if you have a system, your ODE system will be converted into, let's say, a recursive algebraic system. Yeah. So if you're familiar with recurrence relations, then basically numerical methods for ODEs are what? Recurrence relations. So you move from one step into another recursively or successively. Okay. So here, well, people also call this discrete time systems. Yeah. Compared, in contrast to ODEs, which they call, which we sometimes call continuous systems. Well, to have what? An intuition, what we are aiming to do. So suppose blue is the solution curve of your ODE. Okay. So in this case, I think this is some sort of an exponential function. Okay. And you have some sample time. So let's say you divide your interval into 4 equal subintervals. Okay. And the distance between 2 consecutive time nodes would be your step size. So yung length ng subinterval na to would be h. Okay. So we want to approximate these values here, ut0, ut1, until there's a typo here. I think this should be ut sub 4. Okay. So we would like to approximate the solution at the sampled time nodes. Of course, this is what? The unknown. Ito yung hinahanap natin. So these are the unknown. So what we would like is to determine an approximation. So for instance, here, U sub 1, U sub 2 are the approximations. Yeah. So we aim to approximate this one here. Yeah. So in this example, you see that what the error gets larger. Okay, and that is typically what we can observe later in these methods. So what one can do is that if you want a closer or lesser error, yeah, you would try to choose a larger number of nodes. Okay, so probably by bisection, you introduce midpoints of these sampled time nodes. Okay. Yeah. So the goal is to find these approximations. Okay. Now the question is, what if I want, based on this, let's say, approximation, what if I want to determine the solution at a certain time that is not equal to the time node? So paano pag hindi na siya equal sa mga t sub k's? Okay. What you could do is you could probably refine your time grid by introducing intermediate time nodes, or you could probably do linear interpolation. Okay, so in this case, you just connect two consecutive two consecutive nodes, and then look for the equation of the line. Okay? So if you want, let's say, to calculate the approximation on the midpoint of this the point here, then you could just project that to the line there. Okay? So you could do linear interpolation if you want to, let's say, evaluate your or approximate your solution at a given node that is not the same as the time nodes. Okay, so let me discuss some generic aspects. This is, well, not applicable, not only applicable to numerical ODEs, but in fact to any numerical methods. The first one is method development. So here we will see three ways of looking for approximations via either Taylor expansion, differentiation, or numerical integration. So I hope you still remember your calculus. Okay. So kailan papasok yung numerical integration? Okay. My original problem is ODE. How does integrals enter into this picture? What you could do is, of course, you just basically, let's say, apply the first fundamental theorem of calculus to the ODE. So in other words, you just integrate this, okay? And then you will have this integral equation here, okay? So this differential equation is in fact equivalent to this integral equation. So you either approximate the derivative here, or you either approximate the integral. Okay. Once you have a method, you would like to analyze this method here. So we have some sort of consistency, stability, and convergence, and we will talk about these topics in detail later. Yeah. So roughly speaking, this somehow tells you how is your method related to the original problem. Is it stable with respect to errors? And does the computed approximation converge to the exact solution of your given ODE? Okay. Of course, we want these aspects because let's say may nakuha kang solution. How would you qualify that solution? In other words, how is it close to the exact solution? Yeah. And that's the beauty of analysis. Sometimes, as I commonly say to my students, the beauty of analysis is that you can say that something is close without knowing that as something. Okay. So alam mo kung gaano kalapit yung isang, let's say, number, kung gaano kalapit dun sa exact solution without actually calculating the exact solution. And these two parts here is incomplete without the appropriate algorithm design and implementation. Okay. So here you would look for several test examples in that are classical on the literature, and with respect to convergence, we would also look at the orders of convergence. So this is somehow related to the question of asking how fast is the convergence to the exact solution. And okay, data visualization also to give us a better understanding of the dynamics of the system. Okay, so there was a talk in the morning a while ago by Dr. Colliera, and the one, in fact, before the break, where you can visualize this dynamics either using applets or MATLAB. So the examples that I have given this lecture were implemented in Python, okay, and you could download that on python.org. It is well, unlike MATLAB, it is an open source programming language, so you can download it for free. It works in almost all operating systems. So there's one in Windows, Linux, or in Mac OS, let's say. Yeah. So we will not do programming. So I will not show you how to program, but hopefully, if you have time tomorrow, at the latter part of the lecture, I will provide, let's say, some examples in how could we implement the methods that we have that we will discuss in this lecture. And there are more, of course. Yeah. Ano tong dot na to? Well, when you are let's say in applications, if you're application oriented, let's say your ODE models some disease, let's say, yeah, or some sort of a physical system or engineering model. You need, of course, to interpret your results. Okay. So you just parang yung first plenary talk natin. Yeah. You just need to go beyond the numbers. Yeah. So you need to also to interpret kung ano yung mga nakukuha mong numbers dun sa method mo. Okay. But we will not focus on that. Okay, that part here. So this talk only aims to discuss the first two and illustrate some basic features of part 3. Okay. So do we have questions so far? Okay, so if there's none, then let us move to what we call single-step methods. So, okay, so based on this diagram, you can think of this, let's say, as your previous state. Okay, so if k is 0, this will be your initial state. So we want to move from one step into another using only a single step. So yung step dito means it refers to a time step. So you move from one time node into another. And so given, let's say, a solution at the previous time node, I want to determine the solution or approximation of the solution of the next time node. Okay. Well, probably the one of the familiar methods here is the so-called forward Euler method. So given, let's say, an initial initial data, okay, which is, you can think, as I said, it's an approximation of your data of your ODE. Okay, so if you can see a tilde here, just think of that as an approximation of the quantity below it. Okay, so pag may nakita kayong tilde, ibig sabihin approximation. Okay, so think of this as an approximation of your data. Okay. Then we determine the next approximation via this recursive formula. So what we do is take the sum of the previous solution or previous approximation with the step size, okay, times the value of the right-hand side of the ODE at the time node t sub k, and then at your previous approximation. Okay, so this is called an explicit scheme because here you have the previous solution. Okay, so, or in other words, the right hand side here is independent of uk plus 1. Yeah. So paano ba na-derive yung forward Euler method? Okay, there are 3 methods wherein you could derive this one, which is via Taylor's theorem. So we only deal with, let's say, the linear approximation of this one. So what you do is you expand okay, around the previous time node and evaluate at the next time node. Okay. So hopefully you can recall your Taylor's theorem. If not, you could check later. So this is basically what you evaluate at the previous plus h. Here's the difference between consecutive time nodes. Okay, yun lang yung step size natin. Times the derivative plus some higher order terms, which is quadratic in terms of h. Okay. So these terms are not we are not interested in the particular form, okay? But it has something to do with the second derivative. Yeah. We are just interested in this quantity here, h squared. Okay. So if the step size is small, the square is also small. Okay, so we can think of this sum here, or we can ignore this third term and just consider the first two. Okay. Now you use your ODE, so you substitute t to be tk on your right hand side, and you have this equation. Okay. Okay, dahil malayo na yung ODE natin. So let me just recall ano ba yung ODE natin. Recall that your ODE is u prime of t equal to f of t u of t. Okay. So if you replace t to be t sub k, okay, so the derivative is this quantity here, okay, which is basically this one that I've written here. Okay, so doon ang galing yung part na to. And then what you do is you just you just ignore t, and then to have an approximation, you just get the index. So, okay. So typically, yan yung ginagawa. So these are, take note, the solutions, the unknowns, okay? So you replace the unknowns by the approximations. So what you do is you just ignore t, and then you use this as your subscript here. So yun lang yung ginawa natin dito. So this would be changed to u sub k, and as well as this one. Okay. So that's the forward Euler method using Taylor's theorem. Okay. There's another one, which is in fact close to Taylor's theorem, but let us state it separately. This is what we call the forward difference formula. Okay. Yeah. So you can think of this as the slope of the second line passing through the the time nodes t sub k and t sub k plus 1. Okay. So this is the change in the function values divided by the change in the time nodes, which is basically, as I said, h. So you use this slope of the second line as your approximation of the slope of the tangent line at the time node t sub k. Okay. And again, you use your ODE to have this formula here. Okay. After rearranging the terms, okay, so you multiply by h, put this on the right hand side, and you have this approximation here, which is basically similar to or the same to the Taylor's theorem, the one given by Taylor's theorem. Okay, so what we did here, we approximated the derivative. Third and final one is we use the equivalent integral formula. Okay, so you integrate your ODE on the time interval t sub k to t sub k plus 1, and then you approximate this integral by a box rule. Okay, so this is what, let's say, a very simple approximation of the integral, wherein you take the height of the box to be the value at the left time node, t sub k. So you evaluate your function at the left time node, okay? So that would be the height of the rectangle, and then the width would be just the length of the interval, which is basically, as I said, h in this case. Yeah. So again, you replace this by the approximations, and you end up with this formula. Okay. So here we have derived the forward Euler method using three methods: Taylor's theorem, numerical differentiation, and numerical integration. Okay. In fact, during the course of this lecture, we will see that these methods, in fact, constitute several methods in solving ODEs. One could generalize this third aspect here. So one could consider, let's see, a one parameter family of quadrature rules. So by the way, quadrature rules are nothing but numerical integration of formulas. Yeah. So what we do is we approximate this integral by the following formula. So the first one is the length of the interval of integration. So that's b minus a. And then we approximate the height by basically taking a linear combination, or more precisely, a convex combination of the function values at the endpoints. Okay. And here the parameter theta is taken between 0 to 1. And this is what we call the theta method, because here the parameter was customarily denoted by theta. And so the theta method is as follows. So you compute the next time node by basically incrementing the previous one with this formula here. Okay. So we just apply this formula. We replace this by the step size, h. We replace this by the right-hand side of the ODE. Okay, that's f, evaluated at the left time node. Okay, plus theta times the evaluation at the right time node. So in particular, you get the forward Euler method if theta is 0. So if theta is 0, this will vanish. Okay, so mawawala yan. Theta is 0, so you end up with h times f at the time node t sub k. So that's basically this formula here. Okay. So that's the Euler forward Euler method. If theta is equal to 1, you have the backward. So there's a typo here. So the backward Euler method. So mawawala naman ito. This will vanish, and then this, if theta is 1, you end up with this formula here. Yeah. And in between, so in particular, if theta is 1/2, you have the so-called trapezoidal or Crank-Nicholson method, wherein you take the average of the function values at the endpoints. Okay, I think I have a picture here. So basically, the quadrature schemes for the forward, the trapezoidal, and the backward Euler methods are as follows. So dun sa backward, so our goal was to approximate the integral of this function here. So that's basically the area under the curve. Okay. So we approximate this by this rectangle. Okay, the area of this rectangle. So we choose the height to be the left endpoint. Okay. Yun lang yung medyo misleading dito sa term. Okay. So forward Euler uses the left endpoint. For the backward Euler, you use the right endpoint. Okay, so here you use this approximation. Yeah. And for the midpoint, you have the trapezoidal rule, wherein you take the area of the trapezoid determined by these line segments here, and then you have a line segment passing through the two nodes on the curve. So, right? So this would be your base. Parang ano ba yung area ng trapezoid? 1/2 of area of the base times the sum of the heights. Okay. Well, if your trapezoid is in this orientation, let's say. Okay, based on these figures, one might think, of course, that you will get errors. And here you have an overestimation of the area. Here you have an underestimation of the area. Okay. Well, at least in this figure, you have an underestimation of the area. Okay. But based on this, one might expect that the trapezoidal rule seems to be better. Okay. We'll see and confirm this later. Do you have questions? May I ask the moderator until what time are we? 4:15 ba?
4:15, sir.
Okay, thank you. So I need to be quick. Now, the problem is, what if theta is not equal to 0? You will have what we call an implicit method. Okay. And let us recall the theta method in this form. Okay. It is called an implicit method in the sense that the left-hand side is the unknown, and it also appears in the right-hand side. Okay. So yung UK plus 1 dito ay yung hinahanap natin. So if your f is nonlinear, this equation is a nonlinear equation. Okay, so we need to solve a nonlinear equation in order to advance. Okay. So this is basically a root finding problem. So we want to determine, let's say, a solution of this equation, or a root of this equation, yeah, where g is basically what? This function here obtained by, so you can recognize this by what? Transposing all terms here to the left, into the left part, okay? And then you replace the unknown by some generic variable u, okay? So we want to find this value of u, okay? And once you have that value, that would be now your next u sub k plus 1. Okay. So you have this equation here. So you want to find a 0 for this equation. Okay, your function here could be, let's say, complicated. Okay, and by the way, for simplicity of notation, f sub k would be what? The value of the function f at the time node t sub k, and then at the approximation f u sub k. Yeah. So parang function value at the time node sub k. Just to simplify the formulas. Okay. So if your f is complicated enough, it's very, in fact, difficult to solve this by hand. So we need to look for what? Problems in solving nonlinear equations. And there are several methods, okay? So you can, if you're familiar with the bisection method, you could do that. There's also the fixed point method. And there are several methods that is based on, let's say, the Taylor approximation. And I will discuss one of them. It's called Newton-Raphson method. Okay. And it is commonly called Newton method in some texts. But it seems that si Raphson yung unang nag-devise ng method. And there's what? Di ko lang kung chismis. Na ginaro lang ni Newton. Okay, kinuha lang ni Newton yung method kay Raphson. Okay. You could check on that dispute in the history books if you like. Okay, Newton's method is the following. So it's basically obtained from the mean value theorem. So suppose I have two numbers, u and v. Okay, so think of u as your unknown, v as your approximation. Okay, so if you use the mean value theorem, you have this what? Equation here. So basically, this is the equation of the line. Yeah. So sinasabi nito is you can find a line wherein the slope of that line is equal to the slope of the line, or slope at the point of the curve at some some number xi in between. Okay. So this is your mean value theorem. Which you can recall, this is basically what Taylor's theorem, but you just use the first order version. However, this value psi, if you look at the proof of the mean value theorem, does not give you how to compute. Okay? So what we do is, assuming that u and v are close, then we can think of psi to be close as well to v, and we can replace this, or should I say u? Okay? We should replace psi by that number u, okay? And assuming that v is close to 0, okay? So suppose that is close to a root of your function, then you could, let's say what? solve for v in this case. So this is just basically a linear equation. You could solve for v. If this is 0, you could solve for v here. So you transpose this to the left, divide by the derivative, and you end up with this formula. Okay. And this sets up the approximation for the root finding problem. So there's a geometric interpretation indeed. Newton's method. So for example, think of this as your function, and we want to approximate this root here. Okay, the intersection with respect to the x-axis. In this case, it is the origin. So suppose I approximate, or I have an initial guess of the root somewhere here. Okay, which is, let's say, a bit far to the exact root. What a Newton's method do is the following. So first, based on this, you project your initial guess to the graph. In this case, the blue curve, and then you get this the tangent line. Okay. Now, if you replace this by equality, okay, so basically you need to look at the x intersection. Okay. So you just follow the tangent line until you reach the x-axis. Once you reach the x-axis, that would now be your next point. So this is an iterative process. You again project to the graph, compute the tangent line, and then go to the x-axis. You repeat this and hope for convergence. Okay, so based on this figure, it seems that nagko-converge naman yung scheme, and then if you increase the number of iterations, you are getting closer and closer to the root. Okay. So that is basically Newton's method. So you just alternately projecting to the graph, and then the tangent line to the x-axis. And hopefully we have convergence. Okay, so you plug this into the implicit theta method. So this can be quite technical, but let me summarize without going into the details. What you do is you initialize, okay, your guess. Okay, so here the superscript would denote the iteration number in Newton's method. So your initial guess would be the previous function value or previous approximation, and then you just apply Newton's method with this formula here. This is just our function a while ago, and you could easily compute the derivative with respect to u. Okay, so this this ratio here is computable. So you evaluate this function here at the previous guess, and then you iterate. Okay, so you just continue doing this process. At ito yung geometrical interpretation ng iterative process na yun. Okay. However, of course, you need to terminate. You need to terminate when you satisfy these two criteria. Okay. The first one is what? This tells us that there's no significant change in your iterate. So pag wala nang masyadong pagbabago within some tolerance. Okay. So this tolerance here is some number that is set by the user. So kayo yung magsiset nito. And typically, the tolerance is set to a small number. Let's say 10 to negative 10, something like that. Okay. Or you've reached a certain number of maximum iterations. Of course, you need to formulate this in a for loop or a while loop. Okay. So you need to terminate this in order to ano ba yan? Para hindi maging infinite yung loop mo, you need to declare a finite number of maximum number of iterations. So, well, typically this is large, but not too large. Yeah. Say 1,000 is enough, I think, or even 100 is enough. So you need to stop this Newton's method here in order not for your loop to go indefinitely. once you've reached, okay, or you satisfy this criterion here, whatever that index is, that would now be your next iterate. Okay. Yeah. So schematically, ano yung ginagawa pagdating sa implicit single-step methods? So pagdating sa explicit methods, you just go directly, okay, from the previous approximation to the next one. For implicit methods, is that you go into an intermediate step. You can think of this as your initial. So if you go to this state, you can think of this as your initial guess, and then you iterate until you have a satisfactorily approximation of the next value at the time node tk plus 1. So again, you go to an intermediate step, you apply here Newton's method, you do a loop until you are satisfied with the approximation. You use that as your next approximation. So when it comes to implicit schemes, there is an additional cost, okay, that you need to do. Okay, because of that, for example, in the case of trapezoidal rule, what you could do is you could, instead of having an implicit method, you could have an explicit method, replacing this by the forward Euler method. Okay, and that would result to the so-called Hoyne method. Okay, so this is basically trapezoidal, but we replace the right-hand side, the unknown right-hand side, by the Euler's method. Okay, so, and you end up with this formula here. So I just denoted the function value at the previous time node by f sub k. And this is also called the improved Euler method, for certain reasons that will be clear later. Okay, there are two common there are remarks here. This is an example of what we call a two-stage Runge-Kutta method. Okay, so if you are familiar with the ODE 45 that was presented a while ago, that is a version of Runge-Kutta method of order 4 and 5. Okay. We'll discuss that tomorrow. The improved Euler method is also a version of what we call a predictor-corrector methods, where the predictor is the forward Euler method, we utilize here, and the corrector is the trapezoidal. Okay. These are gray areas at this point. I will discuss them in detail tomorrow. So I will skip this for the moment. Okay, so I think I've prepared a lot of material. So let me summarize these results here. So I will not go into the details. So there is some sort of what we call zero stability. So forget about this technical details here. Okay. So sinasabi lang natin dito. Suppose I have a single step method determined by this formula phi. And here we are just considering explicit methods. So you can think of the forward Euler method or the improved Euler method. So this phi here is the formula obtained from the scheme. We say that it is zero stable if, okay, continuous case. With respect to perturbations, solution is stable. Okay. In other words, if the perturbations or the errors are small enough, then the solution or the computed. Okay. I think naging unstable yung connection ko. Is it okay now?
Yes, sir.
Hello? Okay. And naging unstable. Okay. So instability in my connection. Okay. Now, so zero stability tells us that under perturbations or errors of your numerical scheme, the effect is not drastic. Okay, so small changes or small errors lead to small errors also in the computed solution. Of course, you like this because in reality, if you implement this later on a computer, arithmetic in computer is not precise. Okay, and I will probably give an example later in the future. And it's not precise, and you will have some errors there. So that would be zero stability. Well, kailan tayo nagkakaroon ng zero stability? If you have also Lipschitz condition with respect to your function here. Okay, and that is satisfied by if your f in the Lipschitz or if your f in your ODE, the function in your ODE satisfies the Lipschitz condition. Okay, so that's stability with respect to errors. We also have what we call consistency. Okay, so consistency has something to do with the local truncation errors. So think of this as your approximation of the derivative, and this one is the one obtained by your formula. Okay, so your method is said to be consistent provided that this truncation errors tends to 0. Okay, so these are errors between the approximation and the computed value. So basically, you want to look at the largest error. So if the largest truncation error tends to 0, as you let your step size go to 0, then that would be consistent. Consistency would follow immediately, or a sufficient and necessary condition for consistency is the following. So kapag yung formula mo, if your formula evaluated when, let's say, your step size is 0, quote unquote, or if you like, you can pass to the limit, it is precisely the right-hand side of your ODE. Okay. So that's consistency. So it has something to do with the ODE itself. So consistent ka kapag yung formula mo, if you pass your step size to 0, you end up with the right-hand side. So indeed, if you pass to the limit of this expression here, then formally you end up with a derivative equal to the right-hand side of the ODE. So consistency has something to do with what? How does your method is related to the original problem? Okay. And the last concept is convergence. What is convergence? So you could think of this as what? The maximum absolute errors between the exact solution at the time nodes and the approximated solution, or the approximation, tends to 0. So convergent kapag yung approximation mo nagko-converge siya sa exact solution. So when in studying numerical methods for ODEs, this is what the classical equivalence theorem for explicit single-step methods. So for a consistent single-step method, zero stability is equivalent to convergence. Okay. So if you have a method, an explicit single-step method that is consistent with your ODE, and it is stable with respect to errors or perturbations if and only if your approximation will converge to the exact solution. So ito yung sinasabi ng equivalence theorem for consistent single-step methods. Okay. So if you know that your method is zero stable, then what? It is also convergent, and vice versa. So that is what a nice thing here, because sometimes it is easier to prove zero stability than convergence. Okay. And in this case, this theorem is applicable to the forward Euler method and then on the Hoyne method. So, okay, I'll skip at the moment the concept of absolute stability. I think I will just discuss this next or later. Yeah. Let us consider, let's say, what? An example first. So consider the following undamped harmonic oscillator. So it's a second order ODE. So you can think of V as, let's say, some sort of velocity. So this is a simplified version of your pendulum equation. Okay. If you recall, last time, or yeah, during the previous talk, ano ba yung pendulum equation? So the pendulum equation is something like theta plus, what's this? Gravitational constant divided by the length times sine, I think, yeah. Sine theta, okay, equals 0. Oh, okay. So think of the pendulum equation, and then you take, let's say, what? You take V to be an approximation of your so theta around 0. Okay. So here we want to approximate the dynamics around the steady state 0, right? Recall last time there are what, 2 steady states up to what, modulo 2 pi. Yeah. Either the steady state 0 or the unstable state I think pi. Yeah. Here we consider what, an approximation near the steady state theta t. Okay. So in this case, so around the steady state 0, so take note, if theta is small, then sine theta is close to theta, right? If you are familiar with that approximation. So sine theta t is theta t. So if theta is small, then the sine is close to the angle. You could look at this graphically and zoom that one. Yeah. So what we did is we just replace this by v. Okay, so sine theta is close to theta, which is close to v. So you replace this by v. And for simplicity, let's just make this a constant 1. Okay? So let us choose L, the length, to be equal to the gravitational constant. So if that is 1, you end up with this harmonic oscillator. Okay. So basically, yung fraction naging 1, and then yung sine theta naging theta, which is v. So we want to look at the effect of implementing the 3 methods discussed a while ago. The forward Euler, the Crank-Nicolson, or the trapezoidal, and then the backward Euler. So ang na-discuss pala natin so far is a scalar, first order ODE. But as you might know, and I think this process has been discussed last time in the previous lecture. So you denote, let's say, v. You denote u prime to be negative v. Okay. So that's, and then if that would be the case, you just calculate the derivative of v in this case. Or you denote u to be v prime, and then you calculate the derivative of u you end up with negative V. So you could check that this is equivalent to this system. Okay. So indeed, what would be U of 0? So that would be V prime of 0 that is equal to 1. Okay. So we have converted the second order ODE into a system of first ODE. Yeah. Of course, we know an exact solution. You can solve this the solution of this exactly, and it is given by this this function series. So U is just the cosine and V is just the sine. Okay. So ano pala yung goal? Why do we still compute it numerically kung alam naman na natin yung solution? Okay. So our goal is just to see the behavior ng numerical methods kapag alam natin yung solution. Okay? So what should we expect in general na observation pagdating dun sa mga methods na ginagamit natin? Okay. So here is an illustration. So hopefully it's clear. Yeah. So here, ang plinat dito ay yung U versus V. Okay, so if you can recognize the solution, the exact solution must lie on the unit circle. Yeah. So kung mapapansin nyo dito, in fact, yung crank Nicholson or yung trapezoidal rule is close to the exact value. Okay. So the crank Nicholson method gives a better approximation compared to the forward Euler and the backward Euler methods. Okay. When it comes to the forward Euler method, okay, what it does is it spirals outside the unit circle. So as you forward in time, lumalaki at lumalaki yung error. So instead of staying on the circle, you go beyond the circle, okay, outside the circle. So that is the behavior of the forward Euler method. Well, in the case of the backward Euler, you go inside the unit circle. Okay, so papasok naman siya. So here, I think the step size is pi divided by 25. So that corresponds to 25 node, 50, I'm not mistaken here, 50 nodes in this case. So ito yung approximation natin for forward, that's green. For backward, there's red. So hopefully there's no color blind in the audience. And of course, one might expect more nodes, better approximation. Yes, in this case, if you divide it by 2, so you have a better approximation. So you have a lesser error. So in this case, take note that the error here is large. Okay. Now, that error in this case is smaller. So still, it is what? Not the same as the unit circle. In contrast to the Crank-Nicholson method na siya mismo yung nasa circle. Again, if you divide it by 2, you get a closer one. Okay. So you can continue the process, and you will see that this one will converge to this this part here. Okay. So that is the effect of the forward Euler and the backward Euler method. So there are cases wherein you go outside. There are cases that you go inside. Okay. That can be explained, in fact, analytically, in the case of the Crank-Nicholson method. Okay. So I've written here the scheme, the recursive formula for the Crank-Nicholson method, and I just put the previous time node or previous value at the left. Okay. And here you take the average of the function values. So if you apply the Crank-Nicholson method, you have this recursive difference scheme, to which you can take, you could multiply this by this quantity, so that you get a difference of squares. Okay, and similarly for this one. So after some algebra, okay, which you could do later, you could check the details. After some algebra and rearrangement, you could check that the sum of the squares of the succeeding time node is just basically the same as the previous one. So you could go further until you go to the initial data, which is basically 1. So this means that indeed, okay, our solution lies on the unit circle. Okay. Kaya pagdating sa Crank-Nicholson scheme, bakit siya nagstay doon sa unit circle? This is the reason in that case. Okay. You could also do this in the forward Euler method and backward Euler method, and I think it's a good exercise. Can be challenging at first, but you could try it. So a basic or a routine algebra would show us that the sum of the squares of the nodes or the values would be 1 plus h squared times k plus 1. Okay, so if you increase k here, because the step size is positive, this will increase. Okay, so this will increase. So that's the reason why in the forward Euler method, you go outside the circle. So let's go back here. So in the case of the forward Euler, if you increase k, okay, just think of a number larger than 1. Okay, you raise that into some power, you increase the power, that number will increase. So that's the case of the forward Euler. In the case of the backward Euler, you take the reciprocal. Okay, so that's why in this case, so we already know that this is increasing, so therefore the reciprocal is decreasing. So that is why the magnitude, the sum of the magnitude goes inside the circle, because this is less than 1. Okay, so probably you could check this later. You just substitute the formula for the forward Euler, backward Euler, and then you get some pattern, and then you probably use that pattern, and either you prove it by induction or just derive the formula by recursion. Okay, so I will not go into the details, so please check this fact here. So this is what Dr. Colliero, what Dr. Colliero is telling us a while ago. Yeah. So you should not only rely on the numerical solutions, or in other words, the one that you have computed. So sometimes there can be a analysis. There's a better way, and in fact, probably a more elegant way in explaining the behavior of your schemes. Okay. So one could explain that more precisely by this process here. Okay. But of course, again, this is only a simple example, and yeah. If you want to go to consider the real pendulum, okay, my quotation marks, because this, of course, with respect to some simplification. Yeah. But here, let us consider some friction term, which is this constant k. So if you're familiar in physics, Hooke's law, the acceleration is what, directly proportional to the strain rate, and this is basically what, k times the angle theta. Okay, so you have here some initial angle and initial phase, angular velocity phase. So before I end the talk, let me show you some simulation. So let us consider an animation of the pendulum. What is this? Let us consider an initial angle. Okay. An initial phase, let's say initial angle to be what, pi at around 3.14, let's say. Okay. So here, I think it was done by Crank-Nicholson method. So nasa taas yung pendulum, but it is not necessarily pi. Yeah. So let us see what will happen. So recall that a pi is an unstable steady state, okay, equilibrium. So nag-move lang ang konti. So however that if you perturb that angle a little bit, it will go down, and then later, due to friction, it will just stay at the stable steady state. Okay. Yeah, so let's do that again. So ito yung initial state. Okay, and then it will just go down, and then the amplitude will decrease due to friction. Okay, so yung kinonsider kanina in the previous lecture was that, of course, that's an ideal, neglecting air drag and friction. Okay, if you do that, I think the pendulum will just oscillate based on sa phase portrait last time, right? But if you add friction, you will have this damping mechanism, dissipative mechanism that will signify that the pendulum will go to the stable steady state na kung nasaan nasa baba siya. By the way, yung angle is measured with this vertical line here. So if you want to check, for example, if you ignore friction, let's say you set, let us set the friction to 0. Okay, tingnan natin if what will happen here. So it will go down, and then it will just alternately oscillate in this case. Okay. So here, there's no damping mechanism. We could, well, go forever, and this is only the behavior of that pendulum. But of course, that is non-realistic in nature. So you need to add some damping mechanism. So this is what I done in Python, including the visualization. Okay. So probably I could later at the end of this SINISM, at the end of the SINISM, I could give you the links for the Python code so that you could download it and try it later at home. Okay. I think that's it for today. Next meeting, we'll discuss about the order of convergence, and then the region of stabilities of numerical methods. So thank you for today, and see you tomorrow. By the way, kung may tanong, you could ask me right now, or you could email later.
Thank you, sir. So do we have any question from the audience?
Oh, pagod na sila. So baka bukas. Sige.
So we have a few announcement from the AMCS. So please be informed that the deadline for the membership for MSP is before May 15, 2021. So the annual MSP convention is on May 15, 2021. So I think we can end this meeting for today. So mag-picture pa ba tayo? Or so can we open yung Zoom natin to have a picture for today? Okay. So, okay na po ba? Okay. So, 1, 2, 3, smile. On second page po. Wait lang po. Okay, another one. 1, 2, 3, smile. Okay. Thank you po. We will resume tomorrow at 10 a.m. Thank you. Okay. The evaluation form will be posted tomorrow after the set of lectures given by Prof. Gilbert Peralta. Hello. I think some of the lectures will provide the Beamer slides that they have used in their presentation. So I think we might give you a link to those Beamer slides to follow na lang po yung copies ng lectures if ever.